All right, everybody, let's go ahead and get started on our course here. We're going to start by talking about the Enhanced Interior Gateway Routing Protocol. And in this brief introduction, I'm just going to kind of give you an idea of the types of things that we're going to expect to do, kind of a deep dive through discoveries primarily. Those are demonstrations and lab exercises where we're going to be able to see all these characteristics and all these functions and features as we go through this section here. So the first section that we're going to go through is section number 1, which is implementing EIGRP. Now EIGRP, which is the Enhanced Interior Gateway Routing Protocol, is the successor protocol, if you will, to the original protocol, EIGRP, that was developed by Cisco in the early 90s and was kind of really one of the very first interior routing protocols that existed. In fact, RIP and OSPF and EIGRP were actually developed after EIGRP became a very popular routing protocol. But EIGRP has a lot of the different characteristics of some of the more modern and more robust routing protocols that we typically see in environments today, namely OSPF, or Open Shortest Path First. So even though EIGRP is classified as a distance vector routing protocol, the reality is that it's actually more of an advanced distance vector routing protocol, because it takes a lot of the characteristics from our more advanced link state routing protocols. Things like high-speed convergence, the ability to do the partial and bounded port multiple IPv6 and IPX and AppleTalk and IPv4 and so on. So once an EIGRP neighbor relationship gets established, that's when we start to exchange our routing information. We use things like update packets to exchange that information, and then all of that routing information that gets received from the neighbors goes into a data structure that we have, a very important data structure that we're going to spend quite a bit of time talking about, called the EIGRP topology table. We're also going to spend some time talking about the EIGRP dual algorithm, or the diffusing update algorithm, which is used to calculate the best routes to the remote networks. In order for a route to actually go into the global routing information base, or the global RIB, it has to satisfy something called the feasibility condition. And we'll spend some time talking about that in this section as well. This behavior is this feasibility check, or this feasibility condition check, is a loop avoidance mechanism inside of EIGRP to ensure that we can have a loop-free path as well as a loop-free alternate path once we're selecting our feasible successor, which we'll talk about as well. Ultimately, the route that has the lowest metric to the destination, that's going to become the candidate that's going to go into the global routing table, and if we're running Cisco Express forwarding, into the forwarding information base. And then if there are any other routes that remain, they're going to have to satisfy what we call the feasibility condition to become that backup route to the destination network, and would be used automatically without a dual calculation or dual recalculation in the event that the primary route becomes unavailable. So to calculate the best route to the destination, we use a general term called cost to describe that, but EIGRP uses a very sophisticated metric, which by default, based on the K values, which we're going to again talk about later on, is composed of two different variables, the bandwidth and the delay. Now, EIGRP was originally created for IPv4, IPX, and AppleTalk, but it was easily adapted to IPv6 because of its overall structure. So we can configure EIGRP for IPv6 without any major modifications. But one of the things that we're going to talk about in this section here is also how do we do EIGRP named mode, or what we would refer to as EIGRP address family mode. That allows us to kind of combine the configurations of IPv4 and IPv6, but it goes even further than that, because then we have the ability also to do things like wide metrics, where we have an additional K value, and we go from a 32-bit metric to a 64-bit metric to support additional bandwidths and interface types. So in this section, we're going to talk about EIGRP features. We're going to talk about how EIGRP makes sure that we have reliability in the form of sequencing and acknowledgements. We're going to talk about how EIGRP adds routes to its routing table. We'll also talk about how EIGRP named mode configuration is different from the classic mode configuration and what we gain from moving to that address family mode configuration. In this section, we'll also talk about what is configured under different address family configuration modes. How do EIGRP neighbors exchange their routing information? How are EIGRP routes chosen? How do we choose the best path through the network? We're going to talk about how to describe the EIGRP metric and how we do those calculations. How do we actually calculate the metric? We'll also talk about that feasibility condition that allows us to prevent loops in our EIGRP networks. And then we're going to talk about understanding EIGRP path selection. We're going to do most of these things by actually doing hands-on discussions. I will be showing you through demonstrations how all of these concepts work. We're going to spend a lot of time talking about that. So I look forward to seeing you guys throughout this section and throughout this course, so we'll get started. All right, so the first section that we're going to talk about as far as EIGRP features goes is we're going to talk about the specific details of EIGRP. As we mentioned before, EIGRP is an advanced distance vector routing protocol. That means we take the best characteristics of link state routing protocols and we actually combine those characteristics with distance vector. Now, I don't want to suggest by any means that EIGRP is a link state routing protocol. EIGRP fundamentally is still a distance vector routing protocol, which means that it still does routing by rumor. It only advertises to its peers the routes that it's actually using rather than advertising all of the available paths, but it does make good decisions on how to select those paths. And as we can see from the graphic here, a lot of characteristics like partial updates, support for subnetting, the data link protocol support, we'll talk about that in a lot of detail, fast convergence, V4 and V6 support, and so on. All right, and really these are kind of the things that really differentiate EIGRP from traditional distance vector routing protocols, because they do have all of these different enhancements. The protocol itself was developed by Cisco as a proprietary protocol, but in 2013, there was an informational RFC published that allowed Cisco to retain control of the protocol, but also opened up some of the features of those protocols, of this particular protocol, to allow other vendors to promote interoperability and to actually incorporate the use of EIGRP within their platform as well. That is RFC 7868. But EIGRP does, even though it is still fundamentally a distance vector routing protocol, does actually take advantage of some of the link state characteristics that we typically would see with link state routing protocols, and makes it a much more efficient and a much better routing protocol in general. Now, one of the key elements of EIGRP, and we'll go through each of these here in a minute here, but one of the key elements of EIGRP is that it offers very quick convergence, and it always guarantees a loop-free topology, not only for the successor, which is the best route in EIGRP, but also for the feasible successor, which is the second best route in EIGRP. So it does this in multiple ways, and we'll talk about all these characteristics. And I'll, of course, as I'm doing my discoveries with you guys, we'll see how these things are implemented, and we'll do a deep dive into identifying how we can essentially identify these features and functions that are part of EIGRP. So let's start with fast convergence in this particular case. Now, traditionally, distance vector routing protocols weren't very quick to converge. In fact, they were relatively slow. In fact, RIP, for example, takes seconds or tens of seconds to actually converge as it tries to propagate routing information from one router to the other. Now, EIGRP converges very quickly if the design is implemented correctly, because we can implement features like query scoping, which we'll talk about later on. We can also implement feasible successors. We can design feasible successors into the topology, and we can also implement summarization at any point within the architecture. All of these things we'll be talking about as we go into the protocol in more detail later on. All right. But Cisco introduced EIGRP to converge very, very quickly by implementing not only triggered and bounded updates, which we'll talk about a little bit later on in this section right here, the partial update section, but also making sure that the updates contain information that allows us to identify not only the best path, but a loop-free alternate path based on something called the feasibility condition. So if we have gone through the process of forming our adjacency, and then we go through the process of building that topology database, we select our successor path, but we also select a loop-free alternate feasible successor path. If the primary path fails and we've already selected a loop-free alternate feasible successor path, we just simply quickly adapt to the change in that failure condition by simply inserting that loop-free alternate secondary path, that feasible successor, into the topology database as a successor and ultimately into the global routing information base. If there isn't a feasible successor, we send out queries to our neighbors so that we can discover an alternate route, and those queries are going to propagate until either an alternate route is found or until all of the neighbors basically say, you know what, we don't really have a path to that destination anymore. Now, one of the pieces that I've circled here, this partial updates, also means that instead of sending periodic updates like classic distance vector routing protocols do, with RIP and EIGRP, we send partial triggered updates. These updates get sent only if the path changes or if the metric changes for a particular route. It's going to contain information about that changed route only rather than sending the entire routing information base or EIGRP RIB. And then the propagation of those partial updates are automatically bounded. So that means that only the routers that need that information are actually updated with that information. Because of these capabilities, because these kind of link state characteristics were built into the protocol, that means that only the routers that need the information get it, which means EIGRP consumes a lot less bandwidth, which is actually even better than what you would see with even link state routing protocols, where an update is transmitted to all of the link state routers within a particular area. Not only do we create these partial and bounded updates with EIGRP, but we also limit the scope of these messages being propagated by using unicast or multicast updates. We'll send information to 224.0.0.10 if it's IPv4, or FF02:A if it's IPv6. These are link locally scoped multicast addresses, which means to my directly connected peers. There are instances, of course, where we will actually send unicast updates as well, but we do use multicast in a lot of different cases as well. All right. Another thing that is a part of EIGRP, and this is one of the things that we'll spend quite a bit of time talking about, is what is the sophisticated metric. Now, there are two different options here. We've got our classic EIGRP metric, which represents metric values in a 32-bit wide format. That gives us a lot of granularity for some of the traditional networks that we've had in the past, things like frame relay and ATM and maybe a T1 or a Ethernet link or gigabit Ethernet link. But as we've started to progress and we've started to see faster and faster links with more bandwidth and more speed, we had to introduce a wider metric, which was introduced since Cisco iOS 15 actually, which allows us to create this 64-bit metric format, which is what we refer to as an EIGRP wide metric, that allows us to have interfaces with bandwidths above a gig all the way up to 4.2 terabytes, right? EIGRP supports these much faster speeds, but we can still recognize the difference between some of the slower speed links and these faster speed links by using this 64-bit wide metric. Also with the named mode configuration, where the 64-bit metric came into play, we also introduce additional K values, or at least one additional K value, K6. We'll talk about that actually later on as well. EIGRP also supports, with regard to metric and path selection, not only equal cost load balancing, where we have ECMP, or equal cost multipath routing, where we can insert up to 16, the default is 4, but up to 16 equal cost paths with IPv4, and up to 64, I think it's 32 or 64 depending on the iOS, for IPv6 equal cost paths, where the paths can be used as successors if they all have the same metric. All right, but EIGRP is one of the only routing protocols that actually supports UCMP, unequal cost multipath routing, where we can actually use something called variance, and we can apply a variance multiplier to our feasible distance of our successor route, which is our best route, the metric of the best route, to include other paths in the global rib based on the fact that they fall within that variance scope. It's something that we're definitely going to be seeing a little bit later on when we talk about implementing and actually optimizing EIGRP. So we'll see some of that a little bit later on as well. All right. One of the other things that we have, of course, being that this is a more modern protocol, EIGRP is a classless routing protocol. Its predecessor, IGRP, was class full, which means that it didn't send subnet mask information along with the routing updates. So EIGRP is a classless routing protocol, which means that subnet mask information is going to be propagated along with the routing updates. What does that mean? That means that we can support things like variable length subnet masking. We can do subnetting. We can do supernetting in the form of summarization. And basically, we advertise not only the network prefix information, but we advertise the prefix length information as part of the EIGRP route propagation. So we can support things like discontiguous subnets, variable length subnet masking. And by the way, EIGRP as a protocol operates as a flat architecture. When we get into OSPF later on, we'll talk about the spine and leaf topology that OSPF introduces, which provides us a hierarchical architecture or hierarchical structure to the protocol design. But EIGRP is implemented primarily as a flat architecture, which means that we have the ability to manually summarize at any bit boundary at the interface level, as opposed to the on the ABR or the ASBR when we talk about OSPF. All right. EIGRP also has multiple network layer protocol support. It supports both V4 and V6. Of course, it also supported other network layer protocols like IPX and AppleTalk. We don't really see those anymore, but we use these things called PLMs, or protocol-dependent modules. These modules are basically responsible for managing the protocol requirements specific at that network layer for that particular protocol. So very rapid convergence, very sophisticated metric, and EIGRP is really a great routing protocol because it does support all these things. Another thing that EIGRP supports is what we call seamless connectivity across our data link layer protocols. EIGRP does not require any special configuration, unlike OSPF, which we'll talk about later on, to work across any layer 2 protocol. Now, there may be some instances where you may have a non-broadcast network. Now, OSPF would treat non-broadcast networks completely differently than, say, a broadcast network or a point-to-point link or a point-to-multipoint link, And in fact, in OSPF, we make those distinctions. There's 6 different network types that OSPF recognizes. In a non-broadcast network, we may have to manually identify our neighbors, but EIGRP will still function normally over those types of networks. OSPF uses different configurations based on the different layer 2 protocols. Ethernet is going to be treated differently than frame relay. EIGRP operates effectively in all types of environments. It doesn't really matter what underlying protocol we have. It could be a dedicated point-to-point link. It could be a non-broadcast multi-access network. But EIGRP works very well in these different types of environments. It works with different media types, different speeds of interfaces. It allows us to establish adjacencies across all different types of WAN links. And then we can also limit or have the ability to tune EIGRP's use of the bandwidth on these particular links by doing unicast neighbor relationships or by implementing summarization or query scoping across these links. Stub routing features is how we do that, and we'll talk about stub routing features a little bit later on. All right, so those are the basic functions of EIGRP. Of course, in our discoveries, we're going to take a look at all of these characteristics in much more detail as part of our discovery process, and we'll take a look at all of these different characteristics. All right, another concept that's important to understand is the reliability mechanism that's built into EIGRP. One of the key features of EIGRP is that it doesn't rely on any specific transport. BGP, for example, is an application layer protocol. It runs on top of TCP. RIP is an application layer protocol. It runs on top of UDP. But both EIGRP and OSPF actually run directly on top of IP, specifically protocol number 88 for EIGRP. Now, this reliable transport protocol, which is a little bit misleading because it makes it appear as though there's kind of this secondary protocol that's being used with EIGRP. It's not entirely true, actually. The reliability that's built into EIGRP, and we're going to see this in some of our Wireshark captures throughout our discoveries, is really just a sequencing and acknowledgement feature that's built into the protocol. There are 5 major packet types in EIGRP. There's a hello packet, there's an update, there's a query, there's a reply, and there's an acknowledgement. We have some other ones as well, like stuck in active query and stuck in active reply. But because EIGRP runs over the network layer and doesn't rely on any transport layer functions, it needs to have some reliability built into it. And that's what the reliable transport protocol provides in this particular case. It provides that reliability through the use of sequencing and acknowledgements. EIGRP updates are sequenced and acknowledged. Queries are sequenced and acknowledged. Replies are sequenced and acknowledged. We do not sequence or acknowledge hello packets, and we, of course, don't acknowledge acknowledgements. But basically, this allows for reliable and guaranteed delivery of the datagrams in EIGRP. And again, we'll see this in our discoveries. As we start to go through the discoveries, we'll see the whole concept of reliability and so on that's built into this through the use of those sequence numbers and acknowledgements. As I mentioned before, EIGRP will disseminate information, send and receive messages, either by using multicast or unicast. We'll see some of that a little bit later on as well. The multicast addresses specifically that are used with EIGRP are link locally scoped multicast addresses 224.0.0.10. Those messages have a time to live of 1, which means non-routable. FF02, which is a link local scope as well. That's actually what the 2 represents in this particular case. The A is the multicast group number, and the FF represents that it's a multicast address. Like I said, only specific packets are going to be sent reliably and acknowledged. Those would be my updates, my queries, and my replies. Okay, so EIGRP runs directly above the IP layer. It's its own protocol, specifically protocol 88. And it's just a component. RTP is really just a component of EIGRP that is responsible for that ordered delivery of EIGRP packets to the neighbors. And that's what we're really talking about in this case. RTP only sends certain packets reliably, namely the updates, the queries, and the replies, which will contain an indication of a sequence number, and you will see that in Wireshark captures that we will capture a little bit later on, where we also would expect to get an acknowledgement as well. All right, now again, RTP is not a separate protocol. It is a component of the EIGRP routing protocol that allows us to have that reliability. All right, and we'll see more about that a little bit later on as well. Now, as far as EIGRP operations go, EIGRP as a protocol has really three major components. Whenever I teach anybody about different routing protocols, I always tell them that there are three things that you need to understand. You need to understand with regard to the operation of a protocol. Number one, you need to understand what are the routing protocol messages that are used for the protocol to communicate. For example, a hello packet, an update, a query, a reply, an acknowledgement. In OSPF, we have different messages. We have the hello, we have a link state advertisement, a link state request, a link state acknowledgement, a DBD, a database descriptor. In BGP, we have an inform message, or we have an update, or we have a keep alive or a handshake, if you will, with TCP. So there's always going to be certain messages that are used by the protocol for it to be able to communicate information. Three things, right? Anytime you want to learn about a protocol, you always need to know what these three things are. What are the message types that we use in the protocol to disseminate and exchange information? The second thing you need to know are what are the data structures. Data structures is where the information is going to be stored that the protocol is generating and learning from other routers in the topology. You can actually see the three data structures listed here in this particular diagram. You've got your neighbor table. In fact, let me switch over here real quick to my snippet so I can draw for you guys. You've got your neighbor table, right? Now, what goes into this neighbor table? What goes into this neighbor table is all of my information sources, my routing information sources. These are routers that I've actually established an adjacency with. And we'll talk about the restrictions for establishing an adjacency in EIGRP. Some of the basic ones are common subnet. They have to be in a common subnet. They have to be in the same autonomous system number. They have to have the same K values. If we're running authentication, they have to have the same authentication type and the same authentication credentials and so on. Things that don't have to match, which we would see with like OSPF, you don't have to have the same hello and dead timers. There's an MTU consideration, but MTU doesn't have to match and so on. So some differences with link state and distance vector in that regard. But the neighbor table is the first data structure that you need to be aware of. Sorry about that. And let's get this thing back in the center here. Try that again. So you got your neighbor table. Here we go. You got your neighbor table. This is the first data structure that we want to concern ourselves with. Without neighbors, you're not going to learn anything. You're not going to have any information. So obviously, one of the first steps in troubleshooting and verifying EIGRP operations is to make sure that you have neighbors. Now, once I enable EIGRP on a particular interface by using network statements or by enabling the protocol explicitly on the interface if it's IPv6, is I'm going to start generating these hello packets. Hey, that's a message type that we talked about before. And I'm advertising basically to everybody, hey, I'm out here, I'm an EIGRP router, this is my autonomous system number, these are my K values, these are the things that I'm trying to demonstrate. And once I enable EIGRP on this interface, I'll start generating hello packets as well. I'll say, hello, I'm a router. Let's go ahead and become neighbors. So the two routers then become adjacent with each other. They put their information, that information, in the neighbor table. And in our discovery, we'll see exactly what that neighbor table looks like. Now we start to exchange information. We start to exchange routing updates. Here is my complete routing information. All right. Thank you very much for that information. I'm going to go ahead and put that into my topology database, which is my second data structure. This was my first data structure. I'm going to put that information into my topology database, which, by the way, is the EIGRP rib. This is the EIGRP rib, which is specific to EIGRP. All right, that's my routing information base for EIGRP. What do I have in that topology database? I have my successors, which are my best paths. I have my feasible successors, which are my next best paths that meet the feasibility condition. And then I have other route candidates which don't meet the feasibility condition but could possibly be used as alternate paths. We just can't guarantee that they're loop-free alternate paths. So all that information goes into the topology database. Then the next thing I'm going to do, of course, I'm going to acknowledge that information. I'll send that information. And then I'm going to run my dual algorithm against this database, against the contents of that database. And I'm going to extract from that database my best routes, which are called my successor routes. These are my best routes. These are the routes that are going to go into my global rib. All right. This is my global rib, or my global routing information base. And that global rib is everything that I'm actually using. So this particular data structure is not specific. It is technically the third data structure. It's not specific to EIGRP. It is the entire or global routing table. But at that point, we are fully converged and we are able to start routing across the network. All right. So these are the kinds of processes that you have to be familiar with as you're going through the process of understanding the protocols themselves, right? What are the message types that we use to exchange information? And we're going to do a deep dive into those different message types as we go through the discoveries and go through the rest of the lessons here. What are the data structures that are used by the protocol? For example, EIGRP has OSPF has a neighbor table. The OSPF has a link state database, which is considered the topology database. OSPF actually takes routes out of that database and puts them into the global rib. BGP has a neighbor table. BGP has a global or BGP related rib, which is the show IP BGP output that tells us what's in the BGP rib. And then we have our global routing table that includes those routes as well. All right. So let's move on. We'll talk about named mode versus classic mode as well. In fact, let's kind of move down to that section here. Right? What is named mode versus classic mode? Right? What is the difference between these? Now, EIGRP classic mode is traditionally what most people tend to implement when they're implementing EIGRP. You go router EIGRP or IPv6 router EIGRP, and you start to configure everything under classic mode configuration. The problem with classic mode is twofold. Number one, you're stuck with a 32-bit wide metric, which is probably adequate for most enterprises today, but as we start to progress to faster and faster link speeds and more bandwidth, it's going to become less and less effective. So you get that 32-bit wide metric. But the other problem with classic mode configuration is that you have kind of a mixed bag of configurations. You've got some commands that go under the interface, like summarization and authentication. You've got some commands that go under the global routing process, like variants and metric weights and network statements and so on. And so what ends up happening is you start to have kind of what we call a scattered configuration. There's going to be a configuration that is kind of mixed throughout the entire running configuration, if you will. If you go to named mode, right? Named mode provides a concise and complete configuration. The only exception are the keychains, which we'll talk about when we get to the authentication section, because keychains are not really specific to EIGRP. But everything is configured under one section. And you actually name the EIGRP process. So router EIGRP Cisco or router EIGRP my EIGRP. And then we use address families to do the configuration. We have a v4 address family, we have a v6 address family, and then under the address family mode configuration, we set all the properties of the protocol. The nice thing is, though, that you have this complete EIGRP configuration in one individual section. It is also backwards compatible with classic mode. So we have a scaling metric for the global RIB, so that we can make sure that we're scaling down to the metric size that's supported in the routing information base, because the field that stores the metric value is not going to be 64 bits. We also have compatibility with classic mode and named mode, meaning that the two protocols or the two configuration options can talk to each other. But much more accurate support for high-speed links, because we have a much wider metric, powers of 32 bits larger, right, to the power of 32 larger, 64-bit metric. We use picosecond latency for the delay calculations rather than microsecond or tens of microsecond latencies, right? Because as you get to faster and faster speed links, you got to get down to the picosecond calculations. And a very easy to use conversion tool, right? Now, the named mode option became available in iOS 15.01M and iOS 12.2.33 SRE, as well as 12.2.33 XNE, and so on. So pretty much most modern iOS is going to support this named mode configuration. So like I said, we have our 64-bit wide metric. We can do a classic mode to named mode conversion by using the EIGRP upgrade-CLI command, which allows us to kind of migrate or flash cut, if you will, that existing classic configuration without even having to restart the EIGRP process. So we don't even get a flap in the EIGRP process. Once we enter that command, EIGRP upgrade-CLI, the command goes in. It's going to ask us to supply the name that we want to use for the named mode process, and then the name mode configuration gets all the classic configurations, and it kind of puts everything into one place. So let's take a look real quick at a sample configuration, kind of a side-by-side comparison, if you will, of a classic mode versus named mode. So we can see it here, actually. If I was running this in classic mode configuration, I'll highlight some of the configurations that would be applied to the interface versus some of the configurations that would be applied to the global routing process. So for example, these configurations here would be applied to the interface. Actually, the timers as well would be applied to the interface. Bandwidth percent and split horizon would be applied to the interface. Whereas you would have other configurations like passive interface that would be applied in the global routing process, variants, distribute lists, redistribution, network statements, those would all be applied under the global routing process. So there are many different instances where you would have, in classic mode, you would have kind of the configuration mixed throughout your whole running config, and it would be very difficult in this case to really identify. But they do break it down actually here. The blue represents stuff that would be typically configured under an interface. The orange represents stuff that would be affecting the topology table, and the red represents stuff that is basically general configuration. Let's talk about that real quick. We're going to do a discovery later on where we actually see this configuration. In fact, that's one of the very first discoveries that we do. But the first step is we need to specify the name of the EIGRP process. Now you'll also notice here that we have an address family configuration. We don't see V6, but V6 would look very similar to this because the command structure is just about the same. It's almost identical actually between V4 and V6. But you see that we have what we call address family interface options. Now, the wonderful thing about this, you don't see it listed here, but these would be all my interface specific commands, right? Putting a summary on the interface, specifying authentication, changing or modifying the default timers and so on. But what's even more interesting about this is that you actually have an AF interface default. That's not it, but I'm just circling that for some reason. But you actually have an AF interface default, which means that you can apply the same configuration across all of your EIGRP interfaces at once without having to configure each separate interface. So if I wanted to apply a summary to all of my interfaces, for example, or if I wanted to apply different hello intervals or hold times to all of my interfaces, I could use the AF interface default option. The topology base, I always tell my students, anytime you're making a modification to the actual topology table or the topology database, you're going to do this under topology base. What are some of the things that might apply to that? Things like variance, maximum paths, metric weights, for example, which affect how metrics are calculated, which affects the overall EIGRP topology, distribute lists and filtering, redistribution, which is going to affect what actually goes into the topology database. So anything that actually affects the EIGRP topology database would be configured under the topology base. And then the general configurations like stub configurations, network statements, router ID, those kinds of things, those are going to be basically configured under the global address family. The indentation is not perfect here. It really should be kind of matching up with this address family section here, but I guess it's kind of aligned correctly because of the exclamation point here. But anyway, you would go into your global config, you go to router EIGRP Cisco, you would specify address family IPv4 unicast. This is the autonomous system number. That has to match on all of your routers in order to form an adjacency. And that's what allows you basically to identify your AS. It does not have to match between V4 and V6, but it can if you want it to. But these would be kind of your general configurations under the address family. Notice these are all kind of sub-configurations under topology base, sub-configurations under AF interface, and so on. So the wonderful thing is you get to see everything in one kind of grouping, and everything is kind of, in one section, if you will. All right. So what we're going to do now is we're going to go and jump into our first discovery in this section, which is Discovery 1, configuring EIGRP using classic mode and named mode for IPv4 and IPv6. So we're going to get into our first discovery, and this discovery for EIGRP, we're going to be doing EIGRP classic mode and named mode for IPv6. We have 4 routers in this topology. Pretty basic topology, not a lot going on here, as far as any kind of the advanced configurations that we're going to see a little bit later on. We're going to focus, like I said, primarily on classic mode and named mode configuration. So we'll start by doing some classic mode configuration for branch 1 and branch 2. For HQ, we're going to do our named mode configuration. So the first part of the process is to enable IPv4 for EIGRP using classic mode on branch 1. Then we're going to enable IPv6 for EIGRP using classic mode on branch 2. And then on the distribution router, we're going to do IPv4 and v6 dual stack using the named mode configuration. And then we're going to configure BR1 and the distribution router to send out EIGRP updates only through interfaces that are peering with their neighbors, which means passive interface, right? As we talked about the passive interface concept. We're also going to adjust some of the different timers between HQ and BR2. So again, this is our basic topology. Doesn't quite look the same in GNS3 because of the way that the serial interfaces get put in there, but this is what our overall topology is going to look like. And most of the addressing stuff has already been configured. We're not going to be doing that, but that's what our goal is. So they've got some of the information here. Just keep in mind, pay attention during this process to the interface numbers. Again, if it's 00, it's typically going to be 10. Serial interfaces are typically going to be serial 20, but if you look at the topology diagram, everything is documented on the diagram. So just pay attention to the interfaces as you're doing the configuration. Do not just blindly type what's in the actual discovery in the documentation. Pay attention to the interfaces because they did change a little bit. Here's all our IP addressing information. We're going to skip over that. So the first task in this case is to enable IPv4 for EIGRP using classic mode on the branch 1 router. So we're going to enable EIGRP. Our autonomous system number in this topology is AS10 for IPv4, and it's going to be AS20 for IPv6. So the first thing that I would typically do is I would go into the router itself, and let's all go into branch 1 here. And what I would typically do is just try and verify what's presently running on the router itself by using the show IP protocols command. And as you can see, there is no current configuration on this particular platform. I would also do a quick show IP interface brief just to make sure my interfaces are operational. We've got 3 different interfaces, 2 loopback interfaces, and 1 physical Ethernet interface. In this case, we're dealing with Ethernet 10. Just make sure you pay attention to that, and that's going to be part of our configuration. So we're going to go into privilege mode. We're going to go into global configuration mode. We're going to start the configuration of the EIGRP process by specifying the autonomous system number. Make sure that the ASs match. The EIGRP autonomous system number is not just locally significant. It has to match on all the peers, unlike the OSPF process ID, which is locally significant. Now, in EIGRP, you have the option of enabling the protocol on the interface by either using classful network statements or classless network statements with wildcards. Remember, the way that you put the network statements into EIGRP is not how networks are advertised. It is like a light switch. It turns on or turns off the protocol based on what interfaces fall within the scope of the network statement. Right? So 192.168.1.0 without a wildcard means Class C, because 192 is a Class C address. So it basically means any interface that starts with 192.168.1. In the case of 192.168.2, it's the same, but in the case of 192.168.255, they decided to use the wildcard mask. Basically, in this case, the zeros mean I care. The ones, the binary ones in the mask mean I don't care, right? Just like we saw with OSPF in our OSPF section. So .3 means that the last 2 bits of the address can be anything. The first 22 bits of the address, 30 bits of the address have to be 192.168.255. All right, actually the fourth octet's included in that as well. There is no golden rule as to how to enter the network statements, right? It just depends on what your objective is. If you want to enter network statements that are more generic, so it includes more interfaces, you can. If you want to make them more specific, so it includes fewer interfaces, you can do that as well. All right? So let's go ahead and do that. We're going to go into our branch router. So we're going to go router EIGRP. Now again, the autonomous system number is a 16-bit value. Notice here we do have the option of creating a virtual instance name. That's the named mode configuration. Or we can specify the autonomous system number as a 16-bit integer, right? So 10 in this case. All right, now we still have all the standard configurations, but we can, we're going to get into some of those the more specifics a little bit later on. But I'm going to go ahead and put my network statements in. This is for one of my loopbacks. This is for the other loopback. Now, I could have done this. I could have simply gone in here and said 192.168.0.0, 0.0.255.255. And that would have included all of my 192.168 networks. Again, that does not mean that I'm going to be advertising a /16 route, right? It just depends on what's configured on the interfaces. All right, so, and then I'm going to put in a network for 192.168.255.0. Now, here's the interesting thing about EIGRP. They want you to put in a wildcard, an inverse mask wildcard. But EIGRP actually allows you to put in a 224, sorry, actually allows you to put in a, and actually it would be, in this case, a .3 would be 252 in our case. So they actually allow you to put in a regular dotted decimal mask, right? But if I do a show run pipe section router, you'll notice that EIGRP converts that to a .3. All right, it actually will convert it to an inverse mask. All right, so it does allow you to put it in dotted decimal, regular dotted decimal format, but it will convert it to the inverse mask format. All right, so again, the network statements, you can make them as specific as you want. You can make them as generic as you want. It really just depends on what interfaces you want running the protocols, how much control you want. See, a lot of people will say, well, I'll just put in a generic network statement so that it includes 10 or 15 different interfaces. But the downside to that is if interfaces get added later on, they might automatically start running the protocol. You may not want that to be the case. So you may decide to do more specific network statements so you can control specifically which interfaces are going to be running the protocol. All right? Step 2, they also want us to go ahead and configure the router ID. Now, the router ID is going to be selected based on the same algorithm that we talked about for OSPF. Manually configured takes precedence over anything else. If I don't have a manually configured router ID, the next step is what? The highest physical IP address on my loopback interfaces. So if I go into my routing process now, and I do a show IP protocols, I can see what the router ID is presently. And notice it is, in fact, the loopback address, 2.1. I've got a 1.1 loopback and I've got a 2.1 loopback. So the router ID was automatically selected as the highest active loopback. It doesn't have to be part of the EIGRP process. In this case it is, but it doesn't have to be. The third option is what? The third option is highest physical interface IP. So we're going to go ahead and set that router ID. We're still in the routing process. We're going to say EIGRP router ID, and in our case for this router, we're going to set it to 2.2.2.2. It does not have to be an IP address. The router ID does not have to be an IP address, but it does have to follow that 32-bit dotted decimal format. All right, so again, let's do a show IP protocols, and you will see that the router ID, in the case of EIGRP, unlike OSPF, it's preemptive. So the router ID automatically changed. We didn't have to clear the process. We didn't have to reset EIGRP. It automatically started. Okay? Is the router ID as significant in EIGRP as it is in OSPF? No, it's not. So a lot of times we don't really use the router ID too much. In OSPF, of course, it's used for everything. It's used to identify the link state advertisements. It's used to identify peers and neighbor relationships. But it is in the case of EIGRP. not used as often. Now it does say here that the router ID is not changed unless the EIGRP process is cleared. That is not entirely true. We just actually saw that, right? I didn't clear the EIGRP process and the router ID did change. All right. In fact, you see automatically that the route configuration changed, so we actually did a reset, a soft reset on our neighbor based on that router ID changing. So that's not actually accurate. Okay, so now we've got our configuration. We can just take a look real quick. Show run, do show run pipe section router, or EIGRP, either one will work. And this is our V4 configuration. V6 was already configured a little bit. We'll get into V6 stuff a little bit later on. So router EIGRP 10, network 1.0, 2.0, and then 255. Like I said, if you have conflicting network statements, in other words, there may be some network statements that overlap with each other, the more specific ones will always take precedence. All right. In the case of EIGRP, it's not a big deal because we're not putting interfaces into areas, so it doesn't really affect the configuration of the interface. But in OSPF, obviously, because we do place interfaces into areas, if you have conflicting network statements, you might end up putting an interface into the wrong area. All right? All right. So let's see what they say here. IPv4 EIGRP classic mode is configured for AS10. We had, with a wildcard mask for the 4.0 network, we could use a wildcard. Oh, this is BR2. Okay, let's go ahead and go into BR2 and verify BR2's configuration. I was wondering where they were getting the 4.0 subnet from. So let's go over to BR2, which is already configured. So show run pipe section EIGRP or section router, either one works. Router obviously will include other configurations. So yeah, in this case, they did a 4.0, but they did a wildcard of 0.0.3, which interestingly enough, would mean a block of 4. See, the wildcards, because they are an inverse mask, it's not like bitwise masking that we see with access lists, where we could have a .1 or a .12 or a .8 or whatever. In the case of a wildcard mask for network statements, they literally are an inverse mask, which means they have to have consecutive zeros followed by consecutive ones. So you're only going to see like a .1, a .3, a .7, a .15, a .31, a .63, a .127, and a .255. Those are the only values you could possibly see. All right, and those are all basically inverses of 128, 224, 128, 192, 224, 240, 248, 252, 254, and 255. Okay, so a .3 means a block of 4, a .1 means a block of 2, a .7 means a block of 8, a .15 means a block of 16, and so on. So basically this is a 4 with a block of 4, which is 4, 5, 6, and 7. So if I had an interface that was 192.168.5 and another interface that was 192.168.6 and so on, they would be included as part of this network statement. Does that make sense? All right. The 192.168.255, again, without a wildcard mask, it assumes the class. In this case, class C, and then the router ID is established there. All right. All right. And they're talking about the same concept here. It's an inverse mask, which means that it has to be consecutive ones. And in this case, it's going to be 4, 5, 6, and 7 because it's a block of 4 starting at 4. All right? If you want to enable the protocol on every single interface, you could actually use a network statement with this value. Quad 0, which is any IP, and a quad 1 mask or 32-bit mask, which indicates I don't care what any of the bits are. That would be the easiest way to implement EIGRP because it would automatically include every single interface, even ones you add down the line in the future. All right. If you wanted to do a specific match, let's say, for example, I wanted to be very particular, show IP route pipe include connected, I could actually come in here. Actually, let me do my locals. I could literally come in and say, okay, I'm going to go ahead and put in an address of 192.168.4.1 with a mask of 0.0.0.0. What that would mean is that only the interface that has that address would be running the protocol. That does not mean I'd be advertising a /32 route, because I would have to see what is under the interface, show run interface loopback 0. What's actually configured under the interface is what ends up being advertised. All right? So it would actually be a 4.0/24 prefix that would be advertised. You can see that, by the way, if you do a show IP EIGRP topology, include 4.0, you can see that it's actually going into the topology as a /24. All right? We didn't use a /24 wildcard. We used an inverse of basically /1622, right? This is an inverse of /22. So it doesn't mean we advertise a /22. It just means that we're including more than one interface potentially in our network statements. All right? So our next task is to enable IPv6 EIGRP using classic mode on the branch to branch router. All right? So this is IPv6. Now remember, EIGRP is a protocol independent routing protocol. It uses these things called PLMs or packet modules, if you will, to transport routing information. So EIGRP runs natively with v6, with v4, but they do operate as independent transports. We're not going to be, even though we have a dual stack configuration, we're not actually, even in named mode, we're not actually going to be combining the stacks together. So the first thing that has to happen, we're doing this on branch 2, is that we have to enable IPv6 unicast routing. That's going to enable the v6 protocol stack on the router. All right. Now we want to make sure that we go ahead and configure our EIGRP. You could use the same AS for v6 as you do for v4. They do not have to be different ASs. All right. In the case of IPv6, it kind of makes sense to have a different autonomous system just to kind of keep things clear. You know that you're running different stacks and one AS is going to be unique from the other one. But again, they do not have to be unique. These are completely independent processes that are running. All right. So let's go ahead and do that. Let's go in here and say IPv6 router, EIGRP. Again, it's a 32-bit or 16-bit number, 20. And then we're just going to say router ID, EIGRP router ID. And this guy is going to be 2.2.2.2. That was actually already implemented, I believe. No, it was implemented on branch 1. Oops, I'm on branch 2, which is router ID 3.3.3.3. You do want to make sure that the router IDs are unique. If you have conflicting router IDs or overlapping router IDs, that could potentially cause some convergence problems with EIGRP. So make sure that you assign the appropriate router ID based on the configuration. All right. Again, it doesn't actually have to be a legitimate number. You would actually have to, if you only had v6 running on the platform, you had no v4 interfaces, you have to specify the router ID. The EIGRP process cannot start without the router ID being configured, because you don't have any v4 interfaces. The process can't select the router ID dynamically. It has to be statically configured. In our case, it didn't really matter because we do have v4 interfaces that are enabled, but we still want to set the router ID manually. We want that to be predictable, right? Now, as far as EIGRP for IPv6, the router ID is selected the same way, manually configured, takes precedence over the highest active IP address on a loopback versus the highest active IP address on a physical interface. All right. Now, one other thing I want to mention. I don't believe they actually mention it in the book here, is that EIGRP for IPv6 is a little bit unique from IPv4 in that you can actually shut down the EIGRP process. Literally under the EIGRP configuration, we can type the command shutdown, and that disables EIGRP for IPv6. So you want to make sure that you execute the no shutdown command just to make sure that the process is running. All right, they don't mention that in the text, but make sure that you execute the no shutdown command, because I believe certain iOSs actually do have EIGRP shut down by default, so it won't run until you do a no shutdown. All right. Now also, with EIGRP for IPv6, we do not use network statements. In fact, with any routing protocol for IPv6, we do not use network statements. OSPF, ISIS, RIP, EIGRP, we do not use network statements. We actually enable the protocol explicitly on the interface. All right, so notice here, they go into interface 00, in our case it's 10. So we're going to go into interface 10, and we're going to enable the process directly on the interface. We're also going to do that for loopback 0, loopback 1, and loopback 2. So let's go ahead and do that. So interface Ethernet 10, IPv6 EIGRP 20, interface loopback 0, IPv6 EIGRP 20, interface loopback 1, and interface loopback 2. All right. Now, there is a kind of a potential downside to this, okay? In IPv6, it's possible to have more than one network running on the interface. You might have 2 or 3 or 4 different prefixes that are configured, global unicast prefixes that are configured on the interface. That being said, there is no way to enable or disable EIGRP per prefix. It's enabled on the interface, so whatever prefixes exist on that interface are going to be now part of EIGRP. The only way to suppress that would be to do some sort of filtering, some sort of prefix filtering on the protocol. Right. So you mean if you went into the interface and did the IPv6 EIGRP 20 without having EIGRP configured?
If I didn't have anything on the interface, if I didn't have an IP address on the interface yet, do I have to, would it automatically just start broadcasting, or do I have to like?
No, the interface would have to have a protocol stack running, right? You could still execute the command, it just wouldn't start the process on the interface. So now with v6 it is a little bit different, because in IPv6, in fact, you can see here, IPv6 adjacencies are done with link local addresses, okay? Now we didn't get into discussing that as much as we probably should have, but link local addresses are, in this case, they're statically configured, but they're dynamically created as soon as you enable v6 on an interface. So let's say, for example, let's do a show run interface Ethernet 1.1. Let's say, for example, this interface, which is not active in our topology, but this interface I wanted to include in EIGRP, right? So let's say I went into interface Ethernet 1.1. I did a no shutdown. I did IPv6 enable without assigning a v6 global unicast address to that interface. Do show IPv6 interface Ethernet 1.1, you can see here that it actually created a link local address dynamically on that interface. It's done using something called the EUI64 process. It takes literally the MAC address of the interface, splits it in half, drops in the FFFE, and it inverts the 7th bit. And this becomes the link local address for the interface. And if I was to enable EIGRP on this interface, You'll also notice that the interface joins the EIGRP multicast group. It's part of the all hosts multicast group. It's part of the all routers multicast group. This multicast address is used for something called the duplicate address detection process, because we want to make sure that this link local address is unique to this interface. But I am now running EIGRP on this interface. Now, there is no global unicast address assigned to this interface, which means I'm not technically advertising any prefixes. FE80 addresses, or link local addresses, which are actually FE80:/10, those link local addresses are link local, literally link local, which means they're non-routable. So I don't advertise link local addresses to other peers, other EIGRP routers, because there's no need to. In OSPF we do, because OSPF is a node routing protocol. It's not a network routing protocol. So we did see the new LSA type for the link locals, LSA type 9. But in the case, or type 8, excuse me, in the case of EIGRP, it doesn't get included. If I do a show IPv6 EIGRP topology, for example, I don't see link local prefixes being advertised. But this is really important. Notice what the next hop is for each of these prefixes. The next hop is link local. If I did a show IPv6 EIGRP neighbor, the peering relationships are link local. So even though we don't actually advertise link local routes to other routers, we use those link local addresses to perform peering relationships, to exchange routing information with neighbors. We use it as the next hop. The reason why is because link local always exists. You cannot have a v6 interface without link local. Link local interfaces always exist, without exception. Okay? So that's pretty important, actually. Now you'll notice that in the case of the link local addresses that we have on our router, they're actually statically configured, number one. And number two, if I do a show run pipe include FE, you'll notice that, well, it's actually only assigned on one interface. Do show run interface Ethernet 1.0. They statically configured the link local address on the interface. Why would I want to do that as opposed to allowing the link local address to be dynamically created using EUI64? Why would I want to statically configure a link local address? Sorry? You have an IP plan where you defined it? And to an extent, yes, right? I would want to statically define my link local addresses because for me, it's a lot easier to recognize who this is than some random, pseudo-random EUI64 process, right? When you're looking at a link local address like this, it's pretty difficult to identify which router that is. And by the way, I can go into interface loopback 0 and I can do this exact command. Oops, not that one, this one here. And I can go to interface loopback 1 and do the same thing, interface loopback 2 and do the same thing. Interface Ethernet 1.1 and do the same thing. Why? How come I can assign the exact same link local address to every interface? Because they're link local. They're not routable. They don't go from one network to the other. Now, I can't have the same link local address as my peer, but on the local router, I can have the same link local address on every interface because it only applies to that broadcast domain. It does not apply across broadcast domains. So it's actually pretty common to set the link local address manually and just make it the same so that, and then document that address as belonging to that particular router. So that when you're looking at your topology diagram or you're trying to figure out what's happening with routing or you're troubleshooting or whatever, you can recognize that link local address as belonging to that particular router. Does that make sense? All right, a little bit out of the scope of what they're doing here, but again, this is all good stuff. So enable the protocol explicitly on the interface. This is the same as it is with OSPF. But again, the autonomous system number has to match. And you were asking a question, what if I enable the protocol but there's no address, right? We've already seen that if it's a v6, there's always at least one address, link local. With v4, of course, nothing would happen because you have to have a v4 address specified. But on the flip side, what if I enabled this command? What if I executed this command on the interface, but I hadn't configured the global process? Right? I didn't go in and say IPv6 router EIGRP 20. By putting that command on the interface, it will automatically enable the global process for you. It does not require you to go back and then enable the global process to get the routing to work. So that's kind of useful as well. All right. Task number 3, configure IPv4 and IPv6 using named mode on our distribution router. So I'm going to go into my distribution router real quick. And what I want to do on my distribution router is I want to take a look at what's presently configured. So I'm just going to do a quick show IP protocols, and we can see that there is no routing protocol running on this router. Show IP interface brief again, just to confirm the interfaces. In our case, we're dealing with serial 20 and serial 21, so that's make note of that. And then we've got our 3 loopbacks on this router as well, 96, 98, and 100. Okay, so we're going to start the named process, and we're going to give it a case-sensitive, locally significant name of Cisco. You could actually run multiple named processes on the router if you want to. Just like you can run multiple autonomous system numbers on a router, you can run multiple named processes on the router as well. All right, the name does not have to match between peers, although you would typically want it to match just for consistency. But we're going to do our named mode configuration. Now keep in mind, putting in this command, config t router EIGRP Cisco, does not start the process. Do a show IP protocols, we can see we're still not technically running any routing process because we haven't configured the address families. The address families is what allows us to enable the routing process on the router. Address families are where we define our autonomous system numbers. Okay, so that's pretty important as well. All right, so that's the next step that they do, is they create an IPv4 address family, which in this case means that we're enabling EIGRP for IPv4. And this is the autonomous system number that enables the process, which has to match on all of the routers. If I'm running AS10 on my other routers, I have to run AS10 for the address family. So let's go ahead and go do that. We're going to say address family IPv4, autonomous system number 10. Now if I do a show IP protocols, what happens? We can see that the process has started. All right. There is a difference here. Named mode, there is a difference. Notice that we have 6 K values now. K1, K2, K3, K4, K5, and K6. Also notice that we have this thing called a rib scale, which actually allows us to scale the metric down to the value that's necessary for us to communicate to a classic router. We'll talk about this. This is more of a CCIE thing, but we may talk about this a little bit later. Also notice we're using a 64-bit metric, not a 32-bit metric. As far as the administrative distance of the protocol, that didn't change. It's still 90 and 170. The variance is still 1 for unequal cost load balancing, in that case equal cost. Maximum paths is still 4. That's the number of equal cost paths that will load balance over. If I have more than 4, I can only use 4 of them, and so on. Automatic network summarization is disabled, and so on. So as far as the protocol itself, fundamentally it's still the same. Although the metric is slightly different, the protocol pretty much operates the same way. We still have the dual algorithm with the successor and feasible successor. We still have the feasibility condition. We still have feasible distance and reported distance. And the concepts are still the same. The feasible successor is the route that has the, as long as the feasible distance of that feasible successor route is less, the reported distance of that feasible successor route is less than the feasible distance of my current successor, we meet the condition, and so on. So all that stuff we learned about in the lecture still applies in this particular case. All right. Now we could have said unicast versus multicast. We don't get into that in this case. Unicast address families are what we typically use. We can set the router ID. Notice that it is done under the address family. Again, there are a couple of different places we can apply configurations. We can do AF interface if we want to configure stuff that's specific to an interface. We can do topology if we want to configure things that affect the routing database. Or we have just our general address family configurations. Router ID happens to be one of those things that's done under the global address family configuration. But notice we are in IPv4 AF, not IPv6. So I could actually set the router ID differently for the v6 process as opposed to the v4 process. All right. Now, they also, in this case, decided to just do the generic network statement. And notice I got my adjacencies. Remember, those two routers, the ones that we're peering with, they are, or this is HQ actually that we're peering with. HQ, let's go take a look at HQ real quick. You guys can just watch if you like. I want to take a look quickly at HQ's configuration. I think it's named mode. Show run pipe section router. So in the case of HQ, yeah, we're doing named mode configuration. All right. So we can see here that we've got network statement, in this case a classful network statement. We've got the router ID. We're also running AS address family for IPv6. We've shut down EIGRP on this interface. This is the interface that goes to the service provider, and the router ID was specified here as well. Okay. So in the case of our distribution router, yes, we're peering with another router that's running a named mode. But in the case of BR1 and BR2, those routers are running classic mode, and they're peered with HQ. So again, they are compatible with each other. That's what that RIB scaling factor is for, because if I do have to talk to a classic router, I need to be able to scale down the metric so that I understand what a classic route looks like. I mean, if I look at, let's say, for example, do show IP route EIGRP. You'll notice here that let's take, for example, this 4.0 route, right? Now, from this router's perspective, that is the metric for that route, 158.120.0.0. If I go to branch 1 and do a show IP route EIGRP, you can see that the metric is, it's going to be different regardless because of serial versus Ethernet, but it is vastly different, right? We can see here for the 4.0 subnet, it's a much, much smaller metric. That's not because of the fact that it's Ethernet and serial. That's because of a 32-bit metric. We're using a 32-bit metric as opposed to a 64-bit metric. All right? And in the lecture, we'll get into how that metric is calculated. Actually, we'll probably see it as part of the discovery here. All right? All right. So when defining the IPv6 address family, it's important to use the correct AS. AS20 is what we're using. Again, it's still compatible with other routers that are running a classic mode, but we enable it under the interface. All right? So now we're just going to do a little bit of verification. Let's go into our HQ router. We're going to take a look at our neighbors. Now, unlike OSPF v3, where I kind of replace all of my verification commands with show OSPF v3. In the case of named mode or classic mode, the verification is still the same. We still just basically use our show IP EIGRP topology, show IP EIGRP neighbor, show IP EIGRP neighbor detail, etc. So let's start with show IP EIGRP neighbor on HQ. And you can notice here that we know that we're running named mode here because we can see that virtual instance of EIGRP. And in this case, we see address family 10, right? Now, if I did show IPv6 EIGRP neighbor, I would see the same thing for v6, except for it's AS20, but it's still the same named mode configuration. Unfortunately, I can't just say show EIGRP neighbor and see both of them. Unlike OSPF, where we only have essentially one database to establish the adjacency, where we're combining the stacks together, in EIGRP, they're independent. So just keep that in mind. Outside of the fact that we're running named mode, everything else is identical. Right? The host index column here, this indicates which neighbor was established first. Not really significant because as long as we have our 4 neighbors, that's all that matters in this case. This is the actual peering address of the neighbor. Unlike OSPF where we see the router ID, the address column here actually represents the neighbor's physical IP address. This is the exit interface. This is the hold time. Like I said, for EIGRP, and 99% of the time, it's going to be a 5-second hello and a 15-second hold timer. Unlike OSPF, though, those timers do not have to match. All right? The hold timers will actually get negotiated to the maximum value for both peers. Uptime is how long the neighbor's been active. Smooth round trip time, retransmission timeout. These values are used for essentially the reliability mechanism within EIGRP. If I send an update and I don't get an acknowledgement, I'll use these timers to basically determine when I'm going to do my retransmission and so on. And then we can see sequence numbers. The sequence numbers are pretty significant because they indicate how many times the database has changed. Right? We only increment the sequence numbers if we're sending updates, queries, and replies. So we don't update the sequence for hellos and regular kind of keep alives. So you actually don't really want to see that sequence number increment too often because it means that you might have some instability, potentially some instability in your domain. All right, queue count. We also want to see this number as a 0. Queue count would be the number of packets that are queued for a particular peer. You see anything besides 0, that means that you've got some sort of congestion going on. All right, now let's look at the detail. If we add the detail keyword, it gives us a little bit more information, right? Tells us the peer, tells what version of EIGRP they're running, how many retransmissions and retries we've sent, how many prefixes I'm learning from that peer. It's kind of useful, right? Tells us how many prefixes I'm learning from that peer. And then same with this peer here, I'm learning 4 prefixes, and this peer here, I'm learning 2 prefixes, and so on. So that's kind of useful. It gives us an idea of, or an indication of how many actual prefixes we're learning from a particular peer. And we can then correlate that to our actual topology to see if it's actually accurate. All right. Yours might not show up in the exact same order because it just depends on which host came up first. Notice ours is slightly different than the book because we have this host at the top, but it doesn't really matter the order. Like I said, the host index is not really all that significant. Okay. Here's the breakdown. Host index indicates the order in which the peers were formed. Address is the physical address of the peer. The interface is the exit interface. Hold time or uptime, hold time and uptime indicate how long I'm going to keep that neighbor if I don't get any hello packets, and then uptime is how long the neighbor's been active. smooth round trip time, the amount of time in milliseconds required for the router to send a packet to its neighbor and receive an acknowledgement. So we would keep track of this. Obviously, this is going to be measured based on actual actions, right? So I send out my first I send out my first update, I get an acknowledgement. I use that information and in any subsequent acknowledgements to start to measure what's normal behavior. So when I send an update and I don't get an acknowledgement within that window, within that threshold, I know potentially that there's a problem. And I might actually retransmit. So you'll notice that the smooth round trip time and the retransmission timeout, they're different values. 34 versus 204, 20 versus 120, 25 versus 150. Interesting. Let's see something here. 204 divided by, what was it, 34? Oops. 34. Oops. Try that again. 204 divided by 34. 6. 150 divided by 25. 6. 120 divided by 20. I think you guys are getting the idea here. So what's the difference between SRTT and RTO? RTO is clearly a calculated value based on SRTT. Smooth round trip time, let's say I send an update. I expect to get an acknowledgement within 34 milliseconds. If I don't get an acknowledgement within 34 milliseconds, I'm going to retransmit the update, right? Which is what this retrans is. Retrans is how many times. I'm going to keep retransmitting that update until the RTO timer expires, which is basically where I give up. I say I'm not going to transmit to you anymore because I've tried 6 times and you haven't acknowledged me, so there must be something going on. I don't want to continually cycle through update, 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 and never get an acknowledgement. So that's what the RTO value is. It's used to be able to identify when we basically just give up sending that information. All right? I'm not sure exactly what happens when that occurs. I would have to look that up, but that's what the RTO value is for. Okay? Q count, again, that would be a locally significant event. Q count would only increment if I'm having a local congestion problem. Basically, I'm queuing up packets to send to a peer. Anything above a 0 would indicate that I have more than one packet to send to a particular peer. All right, retrans shows the number of times that a packet is being retransmitted. Retries, the number of times that an attempt was made to retransmit the packet. So what's the difference here? Retrans means the packet was actually sent. Retries means that there's a local problem. That means I tried to send a packet and it didn't go out, right? So that's different. And then the prefixes, of course, the number of prefixes that I'm actually receiving from a particular peer. All right, so now let's verify our v6 neighbors. Pretty much the same thing, show IPv6 EIGRP neighbor. The only difference here in this case, am I missing a neighbor? Looks like I'm missing a few neighbors. We'll have to fix that problem. I've got my Ethernet ones. I don't have my serial ones. Let me do a quick show run section router. It's only shut down on 1.0. That's the other thing that I did not mention. You'll notice how with IPv4, we have to put in our network statements, right? We know there's not network statements in IPv6. In classic mode, we enable the protocol directly on the interface. But you'll notice here that we haven't technically enabled the protocol on any interfaces. If I do a show run interface serial 2.0, you're not going to see IPv6 EIGRP 20 on the interface because we don't do it there. By default, as soon as you enable address family IPv6 and assign an autonomous system number, by default, the protocol is running on all the interfaces for IPv6. So you don't actually have to enable EIGRP. You would have to explicitly disable EIGRP by shutting down the we're not shutting down the interface here. We're shutting down the EIGRP process on the interface. Remember how I told you could shut down EIGRP or turn it on? Well, in this case, we're turning it off on the interface. So based on the output in the book here, we're missing these two peers. So let's go ahead and fix that problem. It looks like we're okay with EIGRP for IPv6 on HQ because we're not explicitly disabling it. The interface, let's do a quick show IP interface brief. The serial interfaces are up and up. I should actually even be able to ping 192.168.255.10 and .14, which would be the addresses on the other side. So I'm going to actually go into our distribution router and take a real quick look. We're doing address family. I know what the issue is. I remember now. Show run section router. We did not enable the v6 address family. Now, this could be an error in the book, but I don't recall them having us do that on the distribution router yet. We did skip it. Okay. So yes, it was supposed to be enabled. So let's go ahead and do that. Let's go. How did I know that? Because when I looked at the configuration of the section, I only see IPv4. There is no address family for IPv6. This is the entire EIGRP configuration on this router. And there is no address family for IPv6. So I'm just going to go in here and do address family IPv6, autonomous system number, unicast. Well, we don't need the unicast, but actually let me get out of this mode. Address family IPv6, autonomous system number 20. Now notice what will happen as soon as I hit return. I'm not enabling the protocol. It automatically enabled it on those serial interfaces.
See, I did it, and it was just interesting to see you show it.
Right. Yeah, and you know, that was we saw that right here. We only had two neighbors, right? Where is my HQ output here? So I first noticed the issue, obviously, when I saw only two neighbors. And I could see that it was Ethernet interfaces where I had my peers on my Ethernet, but I didn't have peers on my serial. So I start to go through the process. Okay, is it running on this router? Show IP protocols would have done that as well, by the way. Show IPv6 protocols. I can see that the protocol, the process is running on these interfaces. So that's useful as well. You can use the show IPv6 protocols. You could also do a show IPv6 EIGRP interface. Show IPv6 EIGRP interface will show you which interfaces are running the protocol. Had I done that on the distribution router, nothing would have come up because I didn't start the address family. Now they did want us to also specify the router ID, and in this case for this router it's 4444. I don't know how I skipped over that, but it's good. You get to see some troubleshooting, right? All right. Also, you get to see that by default, and I don't know if this is a good thing or a bad thing. Some people consider it to be bad because you may want to limit which interfaces are running the protocol, but by default, when you enable the v6 address family, it automatically enables the protocol on all of the interfaces. All right? Yep.
Some of the columns say un/reliable. What does that mean?
Un/reliable means those are packets that are sent that, let me show you, let me put it up here. So show IPv6 EIGRP interface. these are like hellos and acknowledgements, right? Unreliable versus reliable. So unreliable would be the number of packets queued, like hello packets queued or acknowledgements queued. Reliable would be updates, queries, and replies, or stuck in active query and stuck in active reply. All right. Still see the same thing. I'm not sure, what pacing time is related to a multicast flow timer. I don't really get in. I haven't really researched those too much, but obviously it has to do with the throttling of the protocol. But the nice thing about this particular output is this column right here. This is very, very useful because it tells you how many peers you have on a particular interface. By the way, if an interface was passive, for example, I came in here and I said, and they'll probably do this in the discovery a little bit later on, router EIGRP, sorry, IP, let's do router EIGRP Cisco, address family IPv6, autonomous system 20, AF interface loopback 0, passive. So again, we do everything under the routing process, but I'm making loopback 0 passive. Do show IPv6 EIGRP interface. What do you think is going to happen? Loopback 0 is no longer listed because it's no longer sending hellos or receiving or accepting EIGRP packets. All right. So again, do show run pipe section router. We can see here that we basically apply all of our configurations within the address family configuration. So this is the entire EIGRP configuration on this router. Nice, concise, congruent configuration. All right, so let's go back to HQ now. We should see, well, we already did our v4 verification. We talked about that. So let's scroll down and go back to our v6 verification. And now I should, of course, see my neighbors. Let's see, there we go. And I've got my 4 neighbors. But again, notice that the peering is done with link local, not global unicast. These routers do have global unicast addresses, but we're not peering with global unicast addresses. All right. Interface, everything else in the columns is the same as we talked about before. The same as v4. All right. Exact same as IPv4. All right. I just mentioned the show IP EIGRP interface command. Again, very, very useful. I'm not going to run it again, but very, very useful to identify which interfaces are running the protocol. But again, you should understand that just because an interface does not show up in this list does not mean it's not part of EIGRP. A passive interface would not show up in this list because it's not transmitting EIGRP packets. But a passive interface would still be included in the topology database, meaning that the networks that are configured on the passive interface would still be part of the EIGRP process. All right. If I do a show IP EIGRP interface detail command, let's do that one. Show IP EIGRP interface detail. That gives us a ton of information. Specifically, what's very interesting about this output, it of course breaks down each interface separately, right? But it tells us the timers that are on the interface, whether or not split horizon is enabled. That's a distance vector concept. We don't see split horizon in link state protocols, but split horizon is basically a loop avoidance mechanism that's part of the protocol. I never advertise a network back out the same interface I learn it on. Some cases I may actually have to do that, like in a point-to-multipoint interface in a frame relay network or something like that, an MBMA network. I might have to do that. So we can see how many reliable multicast packets we've sent, how many reliable unicast packets I've sent, how many unreliable unicast packets I've sent. and so on. You might look at this and go, well, wait a minute, why am I sending unicast? I thought EIGRP was a multicast protocol. It is multicast in some cases. Typically what happens is EIGRP will start as multicast and then it will switch to unicast once it's established adjacencies because unicast packets are more efficient, right? There are times when I will send out multicast. This is a multi-access network. It's a broadcast domain. So if I'm sending out an update, I would typically send that out as multicast because there's other peers that might exist on this interface that would have to see that. 3 retransmissions. Interesting. So I have had some retransmissions. I've also received some packets that are out of sequence. Not a big deal. And I can see for my serial interface, same timers, by the way. All right. Notice what happens if I go, you guys don't need to do this, but if I go into interface serial 2.1 and I say encapsulation frame relay, and then I run the same command, detail, you'll notice that the timers change here. This is what we consider an MBMA network now. MBMA is non-broadcast multi-access, which is like frame relay, ATM, X25. The default timer on slow speed serial links, which is basically a T1 and below. I think I said 768 before, but it's actually T1 and below, 1.544 megs, is going to have a timer of 60 and 180. All right. Again, it doesn't have to match. Timers do not have to match, but the adjacencies failed because we've got mismatched encapsulations, layer 2 encapsulations. But I just want to demonstrate that the timer will change depending on the type. So let me fix that so we get our adjacencies back. No encapsulation frame relay. It'll go back to HDLC, show interface, serial 2.1. The default encapsulation for serial links is HDLC, which is basically a point-to-point encapsulation protocol. All right. All right. Step 8 in the discovery. Examine the V4 configuration and V6 configuration using show IP protocols and show IP EIGRP interface. So we're going to do this on BR1. We already actually kind of talked about this, but I'll just hit it up one more time. Show IP protocols, again, not specific to EIGRP. Show IP protocols will show me all of my routing protocols, but in our case, we're only running EIGRP. Metric weights, K1 and K3 are the only ones that are used by default. The router ID is established, the administrative distance values, maximum paths of 4, number of maximum equal cost paths I'll load balance over, variance is my multiplier against my feasible distance for my successor, for unequal cost load balancing, and so on. Just one point of note here, routing for networks, this will show you how you actually enabled the protocol on the interface. 2 network statements that are classful, 1 network statement with a /30 wildcard. And then the gateways, these are my peers. My gateways or my routing information sources are my neighbors. These are the routers that I'm learning about information from. This is a pretty useful component of this output right here. Last update, meaning when did I receive information last? And that's the 1 minute and 11 seconds ago because I reset that, I changed that serial link. So we lost an adjacency, which means we lost some prefixes. When I brought the serial link back up, we gained those prefixes back and an update was sent out. So we don't want to see that. This number should actually be relatively large, right? It shouldn't be constantly low because that means that we've got some possible instability in our EIGRP domain. Show IP EIGRP interfaces, again, show IP EIGRP interfaces. We can see which interfaces are running the protocol. how many peers we have, same information we saw before. All right? Same thing for IPv6 if we want to do that for IPv6. Now, a couple of our final tasks here. Task 4, configure BR1 and the distribution routers to send EIGRP only through the interfaces that have neighbors. Passive interface, right? Passive interface suppresses the protocol on the interface that is passive, but it still allows that network, that attached network, to be advertised. All right, so on BR1, configure passive interfaces using the passive interface default. Let's go ahead and do that. Remember, we're running classic mode on this router, router EIGRP1, or EIGRP10, excuse me, passive interface default. Now that's obviously going to break EIGRP, isn't it? Because passive interface default means we're making every single interface passive. And then I can simply say no passive interface Ethernet 1.0 if I want to make a particular interface not passive. You can do it either way. You can say no passive interface default and then make specific interfaces passive, or you can do it the other way, this way. It just depends on how many interfaces are passive. If you've got 10 passive interfaces and one that's not, passive interface default. If you've got only one interface that's passive, just make that one explicitly passive, right? So it just depends on, the effect is the same, right? Passive or no passive, the effect is the same. So remember, in our case, we're using Ethernet 1.0, when no passive interface, Ethernet 1.0. Okay? To do the same thing on our distribution router, we have to do this under our address family. I know it looks like it's a lot more difficult. I mean, you'll look at the syntax here. It's pretty crazy, right? You got to go into the process, then you got to go into the address family, and then you got to AF interface default, passive. Yes, it's not as simple. The steps to configure are not as simple. The effect is the same. But again, you have to look at the big picture. Named mode, when you look at the big picture, provides a lot more benefit than classic mode does. So it does require a bit more configuration. So router EIGRP Cisco, router EIGRP Cisco. By the way, if you were to mistype that, it would just start another name. So be careful with that, because you could end up with 3 or 4 different names in there. It doesn't affect you as long as you're not configuring the ASs. But address family, IPv4 unicast, autonomous system 10, AF interface default. So anything that I do in this mode applies to every interface running EIGRP. Of course, that's going to break EIGRP because I just made every interface passive. All right. AF interface, let me get back one here. AF interface serial to 1, no passive interface. AF interface serial to 0, no passive interface. So again, it's the same concept. We're making every interface passive and then explicitly identifying which interfaces are not passive. Remember, don't use serial 0001. We're using 20 and 21. And then they do the same thing for the IPv6 address family. Okay? I'm going to get a little lazy here and do a cut and paste. Right? Same thing, AF interface default, passive. We'll lose our adjacencies, and then AF interface serial 20, no passive. And AF interface serial 21, no passive. All right. The nice thing about dealing with classic versus named, and then of course dealing with v4 versus v6, is you don't actually have to go and relearn the whole protocol. There are some slight differences, but overall it's configured the same way. So again, let's go ahead and verify on our distribution router. We're going to do a show IP protocols. The only reason we're actually looking at this is to see that we now have passive interfaces, and we can actually see that listed here. Notice first we see EIGRP 10, but we can also identify that this is done under address family mode configuration. Because first of all, we see that AF or the VR. Secondly, we see the metrics, the K values, K6. We see the wide metric reference here, the rib scaling factor, router ID, and so on. But you'll notice here, as part of the process, it says routing for networks, quad 0. That's my V4 stuff, though. I'm looking specifically. Oh, yeah, this is part of the V4. So routing for networks quad 0, but look, it shows us which interfaces are passive. If I did a show IPv6 protocols, I would see something similar, except for I would not see specific references to network statements. I would see basically which interfaces are running the protocol and which interfaces are passive. Notice also for IPv6, there is one slight difference with the maximum paths. The default maximum paths is 16 as opposed to 4. The maximum, I believe, is 64. By the way, how would I change that in named mode? If it was classic configuration, I would simply just say maximum paths. Or I would simply say variants under the router configuration. In named mode, router EIGRP Cisco, I go into the topology. I have to go into the actually, let me go into the address family first. Address family IPv4 autonomous system 10 topology. And in fact, I'm going to use the base topology. We're not doing VRFs, so we're not going to use named topologies. But this is where I would specify variants. This is where I would specify maximum paths. And I wanted to actually verify the V6 address family because I think it's 64. Oops, 20. I think it's 64. And so let's go into topology base and say maximum paths. And the max is, oh, in this case, 32. All right. So the default is 16. The maximum is 32. Are you ever going to have 32 paths? Probably not. That would be a pretty robust network, 32 paths. All right, we did that one already, show IPv6 protocols. So now our last task here is to tune the timers between HQ and BR2. Now, this is interesting because they're actually having us modify the timers so that they don't match. Actually, they're making them match. We're going to make them so they don't match because I want to show you how that works. All right, so we're going to go into BR2. The reason why they're doing this here is they're just showing you that a timer configuration in classic mode would be something that's done on the interface, whereas in named mode, it's done under the AF interface. So it's still part of the same global named mode configuration. So let's go into BR2. And remember, we're doing this under Ethernet 1.0, interface Ethernet 1.0. And they wanted us to set the timers to 1 and 5. Now notice that this is the hello timer. This is the hold timer. If I don't specify the hold time, it will just calculate it at 3 times. We're actually changing it to 5 times. So we're going to set the hello interval to 1 second, which is the lowest value that we can set, right? 1 second is the lowest value we can set. If you want sub-second convergence, you need to run BFD, bidirectional forwarding detection. That gets you down to millisecond convergence times. But and our hold time, we're going to set that to 5 seconds. Should you ever change these values? There's really no need. Obviously, with a hello interval of 1 second, we're going to be generating a lot more hellos, 10 times more hellos, actually 5 times more hellos, because typically it's 5 and 15. And we've got a longer dead timer. Well, shorter dead timer in the sense that it's not 15 seconds anymore, longer in the sense that it's 5 times. All right. So we'll go to our distribution router. We're going to do the same configuration here, except we're going to do it under named mode, and I want to actually change the timer value. Oops, config T. So we're not going to follow exactly what's in the book here because I want to do something here. What if I did this? What if I said under AF interface, and in our case we're going to be using Ethernet 1.2. Ethernet 1.2. What if I did this? What if I said, let me put in a hello interval, but instead of putting a hello interval of 1 second, I'm going to put a hello interval of 8 seconds. Oops, let me minimize that. Let's say I put in a hello interval of 8 seconds. Now keep in mind, the dead interval on the other side is 5 seconds. My hello interval here is 8 seconds. Is that going to pose a problem? Potentially it could. Let's see how EIGRP handles that. Because if you think about it, if I'm sending hellos every 8 seconds and the other side is a dead timer of 5 seconds, that's going to be a bit of a problem, right? Potentially. So let's do our hold time. And I'm just going to make it 3 times. So 8 and 8 is 16, plus another 8 is 24, right? So I'll just make it 24 seconds. Now, if I do a show IP EIGRP neighbor, this is for V4. I should still have, did I do this on the wrong router? I did it on the wrong router. All right, let's do that again. I'm supposed to do it on the HQ. Like, why don't I have a neighbor there? All right. Got to pay attention to what router I'm in, or else I'm going to get fired. Changing the wrong configurations here. All right, let's go back and do this on HQ. I'm still going to do the same thing as I did before, which is to set the timers to 8 and 24. And I'm going to do interface 1, 2. It didn't affect my configuration on the distribution router because the distribution router didn't have any Ethernet interfaces. And I'm going to say my hello interval is 8 and my dead interval, my hold time is going to be 24. All right, so again, going back to our original question, is this going to affect the adjacency? Show IP EIGRP neighbor. I see I still have the neighbor, right? I still have my neighbor here, but notice the hold time. The hold time in this case is 4, which basically means 5, because you never see the top value. Notice how the other ones go to 14 and then they go down, even though the timer is 15, because it's literally, unless you happen to grab it right at the microsecond that it changes to the top value, it's always going to go to 14.99, 14.98. You get the idea. All right? So if you look at BR2, do show IP EIGRP neighbors, you'll see that it actually negotiates the timers. They don't match anymore. The hold time is 24 seconds for this peer, and the hold time on the HQ is 5 seconds. So it actually adjusted the hold values based on what it received in the hello packet. Let me go and show you that real quick. We're talking about Ethernet 1.2. If I do my packet capture here, you will see that the hold timer values are actually specified in the hello packet. So I don't need to have them match because I can just simply negotiate them. So in other words, it doesn't affect the operation of EIGRP. In OSPF, the timers have to match in order for us to be able to maintain that adjacency, but not in EIGRP. So let me just grab one here. Hello packet. And sure enough, in the parameters, we see hold time. Hold time is included as part of the parameter. That's the 5-second hold time coming from the one peer. And if I look at the other peer, you see the 24-second hold time that I set. So it's actually, when I say it's a negotiated value, what I mean to say is that it is a value that's sent as part of the EIGRP hello process. Okay? Should you make them match? Yeah, probably. Probably. Again, 5 and 15 seconds on pretty much every EIGRP interface except for interfaces that are non-broadcast multi-access. Frame relay, X25, ATM. These are all considered NBMA networks, and that's a 60-second hello timer. All right. Investigating a show detail. I'm not going to run this, but again, we saw this before. That show detail output will show you what the timer is for that particular peer. Actually, I will show you. And the only reason I'm going to do that, because I want you to see that EIGRP neighbor detail. For that particular peer, we see the values. Neighbor, not show IP EIGRP neighbor detail. I did interface detail. Did I? Interface detail. I did neighbor detail. All right. Show IP EIGRP interface detail. I was like, why isn't that showing up? Interface detail, and we can see here for this particular neighbor the hello interval and the hold time. Now, the hello interval is not actually sent inside the hello packet, only the hold time. How did I calculate the hello interval? Because I'm actually literally getting hellos every 8 seconds. So I know what the hello interval is because that's how often I'm getting hellos from that particular peer. All right. All right. And they go through the process of discussing the default timers. What is the impact of having a shorter hello time and a smaller dead time versus a longer hello time? You get the idea. Less traffic, more traffic, faster reconvergence, slower reconvergence, depending on how the timers are set. All right. Now they want us to take a look at the routing tables for the HQ router. So let's go ahead and do that. Remember, HQ is running named mode, show IP route, EIGRP. And they point out specifically in the book here the routes that are coming from the distribution router, like serial 2.0 in our case, Ethernet 1.1, and Ethernet 1.2. All right. Now, as I mentioned, the metric is going to be different. In fact, if I drill down into a particular route, for example, show IP route 192.168.1.0, we can actually see the metric listed here for the 1.0 subnet. It happens to match the metric listed here, but I should see all of the values. Now, the delay is in microseconds, the bandwidth is in kilobits per second, and so on. But keep in mind that even though we're seeing a delay listed in microseconds, we use picoseconds for the formula. So we'll see that a little bit later on as part of our discussion, how the metric changes when you go to wide metrics. All right. Show IPv6, EIGRP route, show IPv6 route EIGRP. Same thing, Same metrics. Metrics are calculated the same way for IPv6. The only difference here, of course, is link local. And this is what I was saying before about statically assigning the link local addresses, because it's a lot easier to identify which peer it is if the link local address is statically configured and you have that documented as opposed to some pseudo-random EUI64 link local address. All right. All right. So that's the end of that discovery. We're going to be doing another discovery pretty soon here, looking at the topology information. We'll see you guys there. All right, now getting into the next subsection here, 1.7. We just finished up our discovery and kind of did a really detailed discussion of kind of the things that we talked about during the lecture portion of the series here. But we're also going to do that again. We have actually another discovery coming up here pretty quickly where we're going to look at the exchange of routing information, right? We talked about the three major things that you need to know about a protocol. What are the message types that the protocol uses to disseminate information? What are the data structures that the protocol uses to collect and store that information? And then finally, what is the algorithm, or how does the router make decisions based on that information, and how does it choose the actual paths that go into the global routing information base? So the routers exchange information, but before they exchange information, they have to establish the EIGRP neighbor relationship, and the session establishment then gets followed by that exchange of update information through those update packets, which allow us to advertise the routing information from the EIGRP topology table. Now keep in mind that only the best routes get advertised to the neighbors. Unlike a link state routing protocol where we advertise everything that we know, in EIGRP I only advertise to my peers the information that I'm using. So if I have 3 or 4 different options to route to a particular destination, maybe I'm actually learning about that information directly from the source, I'm going to choose a route that will become my successor route for that particular destination, and that is the only piece of information that I'm going to advertise to my peers. So this is a traditional distance vector concept. Traditional distance vector concept meaning that we do routing by rumor. I have to choose my routes based on the routes that you chose, and then my neighbors choose their routes based on the route that I chose, and so on and so forth. All right, so only the best routes are advertised to the neighbor. That means that only the routes that are used by EIGRP, which are my successor routes, the routes that have the lowest feasible distance, they're the ones that are going to get advertised. In addition to received routing information, the topology table also contains 2 other local sources of information. Directly connected networks that EIGRP has been enabled on, either explicitly by using the IPv6 EIGRP command or by using a network statement, or information that's learned through redistribution, taking routing information from another routing information source and redistributing that information into EIGRP through the use of redistribution statements. Redistributing routes is basically a way of just taking routing information from one source and advertising that routing information into a different routing protocol. That's maybe where you might have a situation where you're actually running multiple routing protocols, and you want to basically inject those routes into your autonomous system from for some reason, whatever that reason might be. These would be specific use case scenarios. So again, we're seeing kind of the exchange of routing information. What we're going to do in the next discovery, which is discovery number 2, is we're going to do a deep dive into the EIGRP topology table. We're going to see how those routes are calculated. We're actually going to have 3 separate links that we're going to manipulate to see how routes go into the topology table and how EIGRP interprets the information from these routes, namely the metrics and the metric variables, to decide what's the successor, who's the feasible successor, what is the feasibility condition, and so on. So we're going to use a discovery to actually discover the different packet types, how the topology table is built, and how we elect the best path to a particular destination. So let's get right into it. So we're going to go into our next discovery. In this discovery, we only have a couple of routers that we're going to be working with. We actually have 3 different WAN links connecting these routers. WAN link 1, which is kind of an Ethernet WAN link, which is the 172.16.1.0 subnet. WAN link 2, which is the 2.0 subnet, and WAN link 3, which is the 3.0 subnet. That's actually a serial link between those 2 routers. And the idea of, obviously this is not a very typical topology, but the idea here is that we're looking at how EIGRP chooses the best path. How can we manipulate that information? So we're going to take a look at that. We're going to take a look at the topology table. We're also going to take a look at, in this particular case, how is the successor and feasible successor relationship, how does that affect our routing decisions and so on. So really basic discovery in this case, just kind of verifying the topology table. We're only doing IPv4 in this particular case. We're not really concerned about named mode or classic mode configuration in this particular case. So that's basically what we have. Now, obviously, the topology in the book is slightly different in that WAN link 3 is at the bottom, and that's just simply because we have a serial link. It's going to, GNS3 kind of throws that in the middle there, so we just have that one in the middle. All right. So the first thing that we want to do, EIGRP is already configured on all of these routers. Our only goal in this discovery is to just kind of go and verify how EIGRP interprets the topology. And of course, I'm going to show you some additional things outside of the scope of what they're doing in the discovery in the book, but I want you guys to be able to see some of the other concepts that we've certainly talked about in the lecture. So let's go into our branch router, and we're going to do a quick debug EIGRP packets. And note, we're debugging essentially all of the major packet types for EIGRP. Update, request, although we probably won't see requests too often. Update, query, reply, hello. You certainly won't be seeing IPX SAP, that's for Internet Packet Exchange. Acknowledgement, stuck in active query, stuck in active reply. But the most important ones in this particular case are the update, the query, and the reply. Those are the ones that we definitely want to see happening between the routers as we start to manipulate the topology and as we start to change around the topology. So let's go ahead and do a debug EIGRP packets on our branch router. Let me jump right in here. Debug EIGRP packets. And let's go ahead and continue on with our configuration. So what they want us to do now is they want us to implement EIGRP using autonomous system number 100 on the branch router. Now, they're using actual wildcard masks here that basically are representative of the actual subnet that exists on those interfaces. Again, it doesn't really matter how you decide to implement your network statements as long as the end game or the end result is that the networks or the interfaces that you want to run the protocol are actually running the protocol. So we're going to go into router EIGRP 100. I'll just do a quick show IP route, include connected, and config T, router EIGRP 100. And we're going to do a network of 172.16. Now it looks like in this particular case, we're not enabling it on all 4 networks. We have 4 separate networks here. We've got 2 Ethernet and 1 serial, and they want us to implement it on the 1.0 subnets, which is this Ethernet 1.0 and the loopback. So we're enabling 1 link between the 2 routers to start with. So network 172.16.1.0, 0.0.0.3, and network 192.168.1.0. You actually don't need the wildcard for that one. And the reason you don't need the wildcard for that one is it's a little bit redundant. 192.168.1.0 is class C. The wildcard mask is class C. So it's not really necessary to put the mask. If you don't put the mask, the router will simply assume it's Class C and it'll enable it on that network. So I didn't put the wildcard mask in this particular case. But we saw a whole bunch of messages now going back and forth between the routers. So let me scroll back up here to the top. Let me first do a undebug all, because the hellos are going to continue to generate debug messages as well. But you'll see as soon as I enable the protocol, right here on the Ethernet link between the routers, I start sending hello packets on that interface. For autonomous system number 100, notice that the hellos are not sequenced. I received a hello on the interface, all right, and that's from this neighbor 172.16.1.1, AS100, also again not sequenced. I've added the peer to that interface, all right, and once I added the peer, notice that my adjacency was formed. What do you think is going to happen as soon as I form a new adjacency? I'm going to exchange routing information, and that's the next thing that happens. We start to queue up an update that's going to go out of Ethernet 1.0 to this neighbor 172.16.1.1. This is sent reliably. You can see that listed there in the queue. Sending 1.0, again, sending another hello, which is just a periodic hello. All right. Sending the update. So from the time that the update was queued to the time that the update was sent, a little bit of time passed, right? A couple of microseconds. Then it says here, I received an update as well, and notice the sequence number incremented. Each time an additional update were to come in, that sequence number would increment. And we maintain different sequence numbers for packets that are sent, reliable packets that are sent, and reliable packets that are received. That's why we see a 1.0, and then we see, that's after we received, then we see sending, sequence 1.1, received another update, sequence 2, received an acknowledgement, and that was based on 0.1, which was this update that was sent here. So you can see that the messages are flying back and forth, indicating that we're actually exchanging information about the routing table, about the information about the peers, and so on. I mean, it looks like a lot of information, but if you were to filter out all the hello packets and you were only to focus on the updates, very few packets were actually exchanged outside of those hellos that are sent every 5 seconds. All right. So immediately after you enable EIGRP on the WAN link, which is the 1.0/30, EIGRP starts sending and receiving hello packets. The process of sending and receiving hello packets is unidirectional, meaning that we don't acknowledge them. I send you a hello, you send me an unrelated hello to me from you to give me your information. All right. Hello packets are sent unreliably because they're not acknowledged. They're sent using multicast. When the branch router receives a hello packet from HQ, it forms that adjacency. We saw that in the debug. Let's see. Actually, they have a couple of things missing from this debug, so let's look at ours. It formed that adjacency right here. Let me go back and find it. Right here, added the peer. So that's where it formed the adjacency, and then you see the adjacency come up. All right. Contrary to the process of sending and receiving hello packets, routing updates are sent and received bidirectionally. Updates meaning that an update gets sent, and then we expect to get an acknowledgement coming back from the receiving router saying that I received your update, right? So that means they're always sent reliably, and that means that we should see those acknowledgments coming from the peer in that particular case. Now, if you guys recall, in fact, let me go ahead and do that real quick. We could see all the same information that we just saw if I was to do a packet capture and reset the interface, you would see the same type of packets going back and forth. What I want to do is I want to take a quick look at what's inside the payload and what the headers look like for each of these datagrams. So let me go back, and I'm going to go into interface Ethernet 1.0 and just shut it down real quick so our adjacency goes down. And we'll do a no shut. And we should see in our debug's not running anymore, but in our Wireshark capture, I should see the different packet types. There's an update. There's an acknowledgement, update, 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 update. So we're seeing all that information going back and forth. Let's start by the hello, right? There's the hello from 1.1. There's the hello from 1.2. Looking at this in Wireshark, if you recall, every single EIGRP packet has a standard EIGRP header. That header includes the version, the opcode for the packet type, in this case a hello packet, which is opcode 5, a checksum, some various flags. We don't really spend too much time talking about the flags, sequence number, acknowledgement number, virtual router ID, since we're not running address families, specifically not running VRFs, virtual routing and forwarding. We don't see anything listed here. And then the autonomous system number. These sections that you see here are common to every single EIGRP packet that is generated. Every single EIGRP packet is going to have the same first section. The parameters also would be included in the packet, although the parameters do not show up necessarily in an update. Let's see, go take a look at an update real quick. All right. So here's an update, and actually it is considered an update, but it's just the initialization of the process. The reason why I know it's not a full update is because I don't have any payload information. This is literally just an EIGRP packet header with a sequence number and the init bit set indicating that we're trying to initialize the synchronization process. If I look at a further update down the line, let me go a little bit further down, right here. This is an update that would actually carry pertinent routing information. So notice again, this is where our EIGRP header stops, and then this is the actual routing information that's being exchanged. So this is what I would consider to be the payload of the update packet. It's telling me about the /27 network. They're telling me about the /30 subnet. Excuse me, the 2.0/30, the 3.0/30, and so on. And the 172.16.00/24, which is a loopback. Also notice what's included in the update, right? The prefix and prefix length, the router ID of the router that's originating the route, the wide metric, if the wide metric options were being used. In the case of HQ, that router is configured for wide metrics. And then the destination address, the destination prefix. Next hop, a quad 0 indicating that this is the router that's originating that prefix. It's not some router down the line that's originating that prefix. Okay? So my suggestion would be, if you're going to try to understand fully this process of convergence and the process of what types of messages are exchanged between the devices, always do a Wireshark capture and take a look at that Wireshark capture. Look at what the messages look like. For example, this one right here, hello ACK. This is actually not a hello packet. It's not a traditional hello packet. It is actually an acknowledgement to a previous message. So if I was to say, look at most likely this update here, nope, that's sequence 7. This update here, this is sequence 5, right? This would be the acknowledgement, where is it at? I had it right here. Let me see if it's this one here. I know I saw it earlier. Yeah, right here. Acknowledgement 5, right? So update sequence 5, and of course the next packet you would expect to get is an acknowledgement. This is update with a sequence of 6. So I would expect to see an acknowledgement with a acknowledgement value of 6. I always acknowledge what I received. Another update here with a sequence of 7. And then this should be an acknowledgement of 7. All right. Now replies, well, this is a completely different protocol. Let's get rid of that. All right. Let's see, hold on. Because it did it based on MAC address. Let me clear the filter. And let's do this. Apply filter, selected. Nope. One more time. Apply filter not selected. There we go. Let's get rid of our ARP. Apply filter and not selected. And apply filter and not selected. There we go. All right. So those are all of our EIGRP datagrams that we saw in that very brief exchange of setting up the communication process, but it's a pretty straightforward process, right? The routers are not actually really going through like the down state and the init and the xstart and the exchange, the loading full like we saw with OSPF. They're basically just establishing an adjacency, identifying each other as neighbors, initializing that routing database synchronization, and then completing that synchronization by exchanging the updates. All right. The number after the sequence in the debug represents the sequence and acknowledgement numbers. If you were to look at the debug carefully, you can know that each packet that is sent out reliably has a corresponding sequence number. The acknowledgement confirms the successful receipt of that particular packet. And that's why we see in the Wireshark trace, we see the whole process. Here's an update, here's an acknowledgement, here's an update, here's an acknowledgement, here's an update, here's an acknowledgement. All right. Now we can also run another command, show IP EIGRP traffic. And this command can be useful for troubleshooting maybe possibly instabilities in the topology. For example, these are the number of hellos that were sent and received, which should be relatively close. It just depends on how many interfaces you have running the protocol, how many updates have been sent, how many updates have been received, how many acknowledges have been sent, how many acknowledgements have been received. Stuck inactive we'll talk about a little bit later on when we get into our query scoping discussion, but we don't really want to see stuck inactive too often. That means that in essence we lost our successor and we didn't have a feasible successor. So I sent out a query, but unfortunately the query got stuck, right? I never got a response from my query with a reply, and after 3 minutes, well, we send stuck inactive queries after 1.5 minutes. Stuck inactive occurs after 3 minutes, which forces us to resolve that problem by resetting neighbor adjacencies, which we want to try to avoid. We'll talk about that process a little bit later on. Okay? Now, obviously what I'm looking for specifically in this particular output, I would expect to see a lot of hellos and sent and received. What I would not expect is to see a lot of updates sent and received. Again, and I certainly shouldn't see queries or replies. The only time you see queries or replies is if you lose your successor and you don't have a feasible successor. So we want to try to avoid getting or sending those, receiving or sending those at all cost by either designing in a feasible successor into our topology or identifying where the instability is occurring, why links are failing, fixing that problem potentially. Why would I not want to see a lot of updates incrementing here because updates are only sent when there's a change. And if the updates are incrementing significantly, that means there's a lot of changes occurring. So it can be kind of useful for troubleshooting. If we look at the routing table on BR, so we'll do a show IP route EIGRP, we should really just see the external network, the 209.165.201 subnet. Why does it have a DEX? Because that is a route that's being redistributed into EIGRP from an external process. So the HQ router is originating that prefix from an external routing domain. All right, the D route indicates that this is something internal to the autonomous system. This happens to be the loopback on HQ. Notice we only have one path to that destination. That path is through 172.16.1.1, which is WAN link number 1. Because we haven't enabled EIGRP on the other links. So the D route, the D indicates that this is a route that exists within my autonomous system natively, and it's originated by a router within the autonomous system. And the DEX route means that that is a route that was redistributed from another routing process. Okay. So if you actually go look at HQ, let's do that actually. Pull up HQ. And if we were to look at the routing configuration, show run pipe section router, you will in fact see redistribution implemented. We're redistributing our connected routes. This is the seed metric that we're applying, 15,000 for the bandwidth, 1,000 for the delay, 255 for the reliability, 1 for the load, 255 for the MTU, and we're applying route map LO1 to that redistribution process, meaning that essentially we're just redistributing one specific prefix. So if I do a show run pipe section route map, if I spell it correctly, we'll see that route map LO1 is just matching interface loopback 1. So in essence, we're only redistributing that particular connected route into EIGRP. All right. They're doing some other manipulation here. This route map RM, which is a 2-clause route map. The point of that route map is to manipulate metrics statically so that we can kind of see how EIGRP handles different paths with different metrics. Not something you would typically see in a production environment, but again, this is for this particular lab because they're trying to influence path selection. All right. So next on the branch router, we're going to go ahead and enable EIGRP on the other two WAN links, 2.0 and 3.0. So I'm going to go back to my branch, config T, router EIGRP 100, 172.16.1.0, 0.0.0.3. We did that one already, sorry. 2.0, 0.0.0.3, and 3.0. And we should see adjacencies come up in both cases because it's already enabled on the HQ side. We're just enabling it on the branch side. So now we have EIGRP running on all three WAN links, not really knowing specifically how those links are configured with regard to bandwidth. We want to investigate this, and we need to identify how EIGRP is going to pick the best path, right? We know that EIGRP uses an algorithm called DUAL, the diffuse update algorithm, to calculate the best path. Reported distance is the cost for my neighbor to reach a particular destination. So if I open up my snipping tool here, and let me go back to my topology diagram, and let's capture this snip of this network here. All right, so we got to capture here, this is our topology. And if you recall, if we were to look at this from the perspective of the branch router here, right? There's a couple of values that we have to consider. There's only one value to consider when we're trying to determine what the best path is. Do you guys know what that is? What's the one thing that we're going to consider with regard to determining the best path? Feasible distance, right? What is the feasible distance of that path? What is the feasible distance of this path? What is the feasible distance of that path? And the lower the number, that becomes my successor path. Agreed? But there is also another value that gets considered as part of this process, and that other value is something called the reported distance. Now, in this particular case, we don't have really anything in between. They're just clouds. And clouds are not routers, which means that we're not actually peering. We're peering directly with HQ, which means the reported distance is really HQ's reported distance, isn't it? HQ's originating a route for this guy. It's originating a route for this external network. So it's the one that's going to generate that reported distance. We add this cost here of the link, and that becomes my feasible distance in this particular case. All right, but we're going to investigate this. We're going to take a look at why a particular path was chosen over another. Is there a way for us to manipulate that to force the router to choose a different path? The metric itself is calculated as advertised distance, which is in essence the reported distance, plus the metric to reach that particular neighbor. The best path is the successor. The best path is the route with the lowest overall feasible distance. That one becomes my successor route. The feasible successor route, if you guys recall, is the second best route as long as it meets the feasibility condition. And if you recall, that feasibility condition states that the reported distance of that candidate, of that feasible successor candidate, the reported distance of that feasible successor candidate must be less than the feasible distance of the current successor route. Okay? All stuff that we talked about in our lecture and our previous discussions as well. All right? So the composite metric is generally calculated based on two different values, bandwidth and delay. We'll look at the actual formula here in a little bit, but the one with the lowest overall metric is the successor. If I have more than one route that exists and we verify that that secondary route is loop-free and it has the same metric, we simply load balance. So let's take a look at the routing table. First of all, we'll look at the topology table. Now, if you recall from our previous discussion, show IP EIGRP topology, the topology table is a list, in essence, of all of my successors and feasible successors. All right. So if you look at the output here, let's say, for example, the 209.165.201 subnet. You'll notice it says there's one successor, meaning there's one best path to reach that destination. The feasible distance is 537,600. That happens to be this particular path through that top Ethernet link. But also notice there's two additional paths that are listed. Question is, which one of these paths, if not both of them, is considered a feasible successor? Well, guess what? The numbers in the brackets or the numbers in the parentheses will help you. The first number represents the feasible distance of said path. The second number represents the reported distance of said path. Is 426,496 less than 537,600? Yes. So this path qualifies as a feasible successor. Is 426,496 less than 537,600? Yes. So this path qualifies as a feasible successor. But technically, which one do you think would actually become my feasible successor? The one that's highlighted, right? Because it has the overall lowest metric. The first number in the brackets or the parentheses is the metric. The second number is the reported distance. Remember, reported distance is never used for choosing the best path. We have to consider the entire path metric in order to choose the best path. Okay? Same thing would happen for the loopback. We see essentially the same values. The only difference is the reported distance is slightly less. Remember, this is our redistributed route, and this is our directly connected route on the HQ router. Same thing though. All of these paths qualify as a feasible successor because it says only one successor because there is only one best path. Remember, the successor is the best path. Right? Now, what would happen if a particular path did not qualify? Let's say, for example, this 3.1 path did not qualify. Maybe the reported distance is higher than 537,600. Let me see if I can make that happen. Show run section route map. It looks like we are applying a metric to prefix list PFX and prefix list external. So show run section PFX. That's the loopback. The problem is show run pipe section router. Let me see if the route map is applied with a distribute list. It is not. Trying to see how they applied this. They're setting the metric for the 00/24 show run section EXT. And that's matching the external route. So they must be applying serial 20. They must be applying, maybe not yet. Maybe it's something that we'll apply a little bit later on. It doesn't look as though the route maps are actually applied anywhere. The route maps are manipulating the metrics for particular prefixes. The only route map that's actually applied, though, is LO1. And I don't see the route map applied to interfaces, no distribute lists. So it doesn't appear that this RM route map has been applied yet. Most likely they're going to have us apply it a little bit later on to affect the overall metrics. So we're going to table that discussion for now because what I was going to try to do was to manipulate this database so that one of the routes did not qualify as a feasible successor. If they don't do this before the end of the discovery, I will show you guys how to do that. And there's a specific reason why I want to show you that as part of this discovery. I want to show you how we analyze the database and actually find those routes that don't qualify as feasible successors. That's very, very important. All right, very important. So if you look at the topology database, one of the things that you will see inside that database, show IP EIGRP topology, is a code. And that code right next to the prefix should always be a P. P means passive, meaning that we are not trying to reconverge. The only other one that you might see if you're really, really lucky is an A. When I say lucky, I mean you just happen to capture the output right in the middle of the process of a query being sent out and a reply coming in. Active means that we lost our primary route, we did not have a feasible successor, and we're now actively searching to see if a secondary route qualifies as an available route. It's a loop-free alternate route. All right? So you could potentially capture that if you were bringing down an interface and refreshing the database very quickly. You might see that active state, but you should not see it very often because active actually literally means that we lost the route and we now sent a query and we're now trying to find an alternate path to that destination. All right? So they want us to take a look at the routing table on BR1 as well, which I believe we already pretty much did. Well, we looked at the topology table, show IP route, EIGRP, and we can see the two prefixes, 409.600, 537.600. All right? So if you recall the metric, let me show you guys how this metric is calculated. So let's say I've got this topology here. Let's clean it off. I've got this topology here, and we're using the top link as our primary path to reach that 00 subnet. All right. And it appears in our routing table that the metric to reach that destination is 409.600. Okay, so we're going to put that on our diagram here. Make that a little bit bigger. Maybe. It's thinking. So that's the metric that's calculated for that particular path. Now the question is, how did we determine that metric, right? Remember we talked about EIGRP, or any routing protocol for that matter, chooses the best path based on the lowest metric, and the metric is always going to be based on egress interfaces. Always going to be based on egress interfaces. So in our particular case, we're talking about this interface right here, and we're talking about the actual loopback on HQ. So in order to calculate this metric, we need to look at the values of those two interfaces to determine what the overall path metric is going to be. So I'm going to go into my router here, my branch router, and I'm going to do a quick show interface, Ethernet 1.0. That's that one link. And I'm going to copy these values right here. That's my bandwidth. That's my delay. All right? And we'll simply put that right here. The bandwidth and the delay for that particular interface. Now I want to take a look at what the loopback is on the HQ router. So I'm going to go over to the HQ router, show interface loopback 0. And this is the bandwidth and the delay for that interface. Everybody understand that those would be the only numbers that would affect the path metric for that particular path. We didn't count this egress interface here because this is a layer 2 link. This cloud does not represent a layer 3 hop. So we don't count this egress interface here because it's not part of the layer 3 path. I mean, it doesn't represent a hop in the layer 3 path. All right. Now, from our previous discussions about EIGRP, do you guys recall what the metric was? Remember, it was that big complex metric with all the K values and the formula and whatever, but what did it end up being after we kind of took out all of the zero values, the K0 values? It was bandwidth and delay, right? And bandwidth was the worst bandwidth along the path which in this case would be 10,000 kilobits per second. The worst bandwidth along the path, take 10 to the power of 7 and divide by that number in kilobits per second, and that gives you the bandwidth calculation. So I would be taking 10 to the power of 7 is that number, which happens to be 100 meg. And then I'm going to divide by, actually, less 10 megs. I'm going to divide by 10,000, which gives me a calculation. So bandwidth equals 10 to the power of 7 divided by the bandwidth min, right? Minimum bandwidth along the path in kilobits per second. So the bandwidth ends up being this number. Let's do the calculation one more time. I think it was 1,000. There's my 10 to the power of 7 divided by 10, 1, 2, 3. Yeah, it's 1,000. Okay. The delay, do you guys remember what the delay was? It was the sum of all the delays in microseconds along the path divided by 10. So that would be 1,000 plus 5,000, which equals 6,000. So we'll take that number, we'll just do it all together here. Take this number here and divide it by 10, because we need that in tens of microseconds, which is going to equal 600. And then the metric is basically bandwidth plus delay times 256. So we have 1,000 plus 600, which equals 1,600. Multiply that times 256. The metric is going to equal 1,600 times 256, 409, 600. See how that works? Why is this important to know? Because if I'm trying to influence path selection, I need to know at what points in the network I can make changes that will influence the path selection. In other words, I could change the bandwidth of this loopback, but guess what? That would affect the metric. First of all, wouldn't have any real bearing unless I change it to something less than 10,000, because it's the worst bandwidth, always the worst bandwidth. But also, changing this interface affects all three paths, doesn't it? Because the metric that's applied to this interface is part of all three paths. So in essence, from branch 1's perspective, there's only one place that I can make a change to affect the path selection for that particular route. Make sense? Thankfully, we don't have to do these calculations on the fly. We can just allow the formula to do the calculations. But I just wanted to show you guys how that calculation was done. All right? All right. So next thing they want us to do is they want us to use the all-links output. Now this is one thing I was going to demonstrate earlier. They're doing this on branch or HQ? Branch, okay? When you run the command show IP EIGRP topology, all it shows you are the successors and feasible successors. It does not show you the routes that did not qualify as either. If you add the all-links on top of that, you will see even the paths that don't qualify as successors or feasible successors. And we can actually see one. Do we actually have one? It looks like for the 3.0 subnet. So if you look up here, well, it is connected. The feasible distance is 128.256. even though it is connected, sorry, 3.0, 216.9856, even though it is connected, we do have alternate paths to that destination. Okay? Remember, we have a couple of loops in the topology here, but this is a perfect example of the loop avoidance mechanism with the EIGRP. 216.9856 is the actual feasible distance of the path that's connected. So because 216.9856 is not less than 216.9856, these two paths don't qualify as feasible successors. But it kind of makes sense, doesn't it? Because those two paths include the original path, basically, which is the serial interface. So they fail to meet the feasibility condition. All right? It doesn't necessarily always mean that an alternate path should not be available. It just means that we have to go through another process in order to verify that alternate path if the primary path fails. So we see a couple of examples here. Let's see, the 201 has 3 routes. Those all qualify. The 2.0/30, that's going to have a couple of routes that didn't qualify because the reported distance of those paths is equal to the feasible distance of the path itself. Remember, in order to qualify based on the feasibility condition, it has to be less. Not equal, but less. Okay? The show IP EIGRP topology all links command displays all possible paths in addition to the successors and feasible successors. Now they called out specifically the route to the 00 subnet has 3 possible paths. Let's take a look at that one. The 00 subnet is here. Yeah. But something is not right because it has a reported distance of 256,000 via 3.1. So something is not applied correctly here. What I was trying to figure out here is why the metrics aren't showing up the way they should be showing up here. If you'll notice from their output in the book here on the branch router, the 1.1 is 537.600.426.496, which is correct in this particular case, 537.600.426.496. The 2.1 is 179.2,000 and 429.6.496. And that looks correct there, but this one here, 3.1, the distribute list is not being applied for some reason. They're intentionally trying to inflate the metric of this particular path for the purposes of demonstrating the fact that it isn't a feasible successor, right? And it says that the metric is 256,000,000, but here we just see the regular metric of 426,496, 2425856 is also not correct. Now the way that they tried to influence that is on the HQ router. We did apply the distribute list in this case. It wasn't applied before, but they've created this route map that basically says for these particular prefixes, we're going to set the metric to a specific value. And we're going to apply that route map using a distribute list, apply the route map out for all the routes that we're advertising out of serial 20. But for some reason, the route map is not being applied, and I'm not sure why. me do a no router EIGRP 100. Just blow away the config real quick. And let me paste it back in. And check one more time on the branch here. Now there's another way that we could kind of influence this. Did that do it? Let me see. Nope, still didn't do it. There's another way we can influence this, but I'm going to table that for right now. Let's just go ahead and use this as our reference. I'll have to figure out why it's not working. This is the official config that's provided by Cisco, so I'm not sure why it's not working in this particular case. But clearly this path here does not meet the feasibility condition, right? This metric, the reported distance of this path, is way higher than the feasible distance of the primary path. And that's really the point they're trying to make. Because of this high reported distance, it's greater than the feasible distance of the primary path. It doesn't meet the feasibility condition. Now, in our particular case, it does meet the feasibility condition because the metric's not being modified for some reason. It should absolutely work, though. Not sure why. But anyway, you understand the point of the demonstration. So what we did here is I'm not sure why the actual distribute list isn't working. It should technically work. So just to kind of get the numbers to be close, I just applied an offset to the routes that are being advertised to this particular peer. And I calculated this number based on what the actual reported distance was versus what the book had, and I did an offset. It did offset the overall feasible distance as well as the reported distance, so it doesn't quite match. We've got 256 512.000, and then this is the reported distance. And if we look on our branch router here, we've got our 256.00000, a little bit higher on the overall feasible distance. But in any event, it's the same result, right? The result is that this third path now does not qualify as a feasible successor. So if the path through 1.1 fails, what's going to happen in the convergence process? Does this path through 2.1 meet the feasibility condition? Yes. 426.496 is less than 537.600. So what's going to be the result of the primary path failing? The second path will be inserted into the routing table immediately. Without doing a query, without sending getting a reply, we're going to go ahead and use this backup path immediately. What would happen if this path would fail? Do I have a feasible successor at that point?
Yeah.
I do?
Well,
I don't. 1.1 is already gone. 2.1 and 3.1 are the only available paths at this point. Do I have a feasible successor? No. This number is way larger than this number. The reported distance of this secondary path is larger than the feasible distance of the primary path. So what's going to happen if the 2.1 path fails? We're going to send a query. We're going to get a reply from 3.1 saying, yes, I still have a path, and then I will insert that path into the routing table. It's in the size of the network that we have, almost instantaneous. If you have lots and lots of peers that you have to query, and then they have to query their peers, and then they have to query their peers, it could take a couple of seconds, but it's usually a pretty quick process. Okay? So we kind of tricked the router. Again, I'm not sure why the distribute list is not working. I think it's a GNS3 thing, but we found another way, so that's fine. Okay? So what they want us to do is they want us to do a continuous ping on the branch router to that loopback on the HQ do not do 100,000 pings. There's no reason to do 100,000 pings. Just do 500 pings or whatever. We don't need to do 100,000 pings. So I'm going to just do a repeat of 500. I'll still do a size of 1,000 because I want to generate kind of normal size datagrams. All right, we're going to repeat and we'll just do a size. I'll just do a size of 1,200. So I'm doing my pings, right? And the pings are going through. What they want us to do now is they want us to shut down Ethernet 1.0 on the HQ router. You might have to actually do more than 500. I didn't do it quick enough. Let's do 5,000. 100,000 definitely is not necessary, but let's do 5,000, right? Now the idea here is that if I shut down Ethernet 1.0, that the branch router should eventually fail over to the secondary link. But you'll notice here, I'm getting timeouts, right? You're thinking, well, wait a minute, I shouldn't be getting a bunch of timeouts and then everything starts working again. This is not a failure of the dual algorithm. This happens to be based on the dead timer that exists between the two routers. Because if you look at the topology diagram, there is a device in between. This cloud, there's a device there. This cloud is actually a hub that I just changed the symbol for. So turning this interface off did not change this interface's status. So from Branch's perspective, it thinks that that network is still reachable. So we have to wait for the dead timer to expire in order for us to create that failover event, because the neighbor has to go down. How can I fix that problem so that we don't have to wait as long? Change the timers. I could create shorter timers. Secondarily, I could do something called implementing BFD, bidirectional forwarding detection, which is basically like a keep alive or heartbeat mechanism that runs across the line, but it works in sub-second timer values. So we could actually have convergence in sub-second speeds if we were to implement something like BFD across that link. All right, but we are now using that secondary link. So if I do a show IP EIGRP topology, we can see that the 2.1 link is now the successor. If I do my all dash links, I still have the other path as well through through router 3, but again, it still doesn't qualify as a feasible successor because the reported distance of this path is much, much larger than the feasible distance of my primary path. All right. So now this top WAN link is disabled and only the 2 links remain. So they did the same thing here. They did a shutdown. Now notice HQ basically said, yeah, that neighbor doesn't exist anymore. Because HQ is smart enough to say, well, if the physical connected route doesn't exist, then the neighbor can't exist. So the connected interface goes down. The neighbor that was associated to that connected interface is automatically deleted because the router doesn't have to wait for a dead timer to expire. It knows that physical network doesn't exist anymore, so there's no way that that neighbor can exist. But on the branch side, it takes a little bit of time, and you can see here actually holding time expired. That's the only time where reconvergence occurs and we get our pings back. Okay? And that's what they mention here. As you shut down the Ethernet interface on HQ, the interface instantly changes to down. The EIGRP process on HQ cancels that neighbor relationship on that interface. But remember, we have a 15-second hold time. Did it take 15 seconds for the failover? It depends. You might have already been halfway through the count, the hold time count. Maybe you were down to 12 seconds or 11 seconds. And it would have been a very quick convergence, or if you just happen to start at 15 seconds, just because of timing, it would have taken 4 or 5 seconds for the failover to occur. All right. This is a really, really important concept, and this paragraph describes exactly what I was describing. A common, very common actually, real world situation is that the layer 2 status of the link does not reflect the operational status of the neighbor. All right, if there is a need to speed up convergence, the timers can be adjusted, or you can use some other status detection mechanism. Quite frankly, the most common status detection mechanism is BFD, bidirectional forwarding detection. It's very, very minimal. I don't know specifically the value, but it is the keep alive mechanism is pretty fast, obviously milliseconds, but it's relatively benign. All right. So again, if I go to my branch router now and I look at my routing table, show IP route, EIGRP, we still have a route 1664000 is the metric, but it's still a valid route. No problem. Okay. The former feasible successor route that went over the 2.0 link becomes the successor route and is installed in the routing table. Again, if we look at the topology, if we just did show IP EIGRP topology, we would only see one successor. We would not see a feasible successor because the route through the 3 subnet doesn't meet the condition, which we fixed. So now they want us to do another ping. I'm going to try and do something very unique here. I have to be pretty quick. But we're going to do another ping, and we're going to shut down Ethernet 1.1, which means that the only remaining interface is going to be the serial interface. The same thing's going to happen. We're going to get 5 or 6 packets that get lost because potentially up to 14 packets get lost. But depending on where you are in the cycle of your timing, your counting. But I want to also see if I can capture the active concept, because the branch router should go active once it realizes that the neighbor doesn't exist anymore. I have to be very quick though. So what I have to do is I'm going to queue up my shutdown here. Interface Ethernet 1.1. So I'm going to queue up my shutdown. I'm going to do my ping. Actually, you know what? I'm going to have to do something a little bit different here. Let me do something here. Config T, enable secret Cisco, line VTY04. You guys don't have to do this. Password Cisco. I want to see if so what I would have to do is do a telnet, and let me go over the serial. The serial link is 172.16.3.2, I believe. Yeah. Control Shift 6X, resume. No. I don't know if I can do this or not, but let's give it a try. All right. So I'm going to queue up my shutdown. I'm going to go ahead and do the ping on my branch router. What I'm trying to capture here is the active state. Show IP. I didn't do it fast enough. I won't be able to do it. It's just too much. What I would have to do is I would have to see. It's already put the other route in there. We could do a debug, but maybe they'll have us do that as part of the discovery. But basically, as soon as the branch router determines that the path is down, the successor path is down, the route is going to go into an active state, and the branch router is going to generate a query. Right? The branch router would generate a query, and right when that query gets generated, the route gets marked as active. All right. And that is the challenge that we have. Let me see if it'll allow me to open up another console session. It'll probably give me the same prompt. That would be the only other way. Yeah, it's just going to give me the same prompt. So I'm trying to think, but you guys get the idea. Where the route would go active. All right. So we don't really see, because you were asking the question, how long is that process, right? In this case, I mean, we're talking about a millisecond, couple of milliseconds, basically, well, probably about 30 milliseconds, based on the smooth round trip time, is about how long the route would stay active. So, but it's less than half a second for sure. All right, but you understand why we would go into an active state, because as soon as we detected that the neighbor was down, we no longer have that primary route. In addition, we don't have a feasible successor. So we now have to send a query, and then based on that query, we'll be able to insert the route. We certainly will be able to see the query. If I did this, debug IP EIGRP packet, events, sorry. EIGRP, debug EIGRP, not IP, sorry, packet. All right. Let's get out of this telnet session here. So I'm going to do a no shut. I'm going to bring that interface back up. The branch router should move to that interface relatively quickly. It's still doing the pings. They're much faster over the Ethernet link than they are over the serial link. But let's go ahead and kill the ping. Let me go ahead and shut down the interface, and you will see the query being sent. So I've canceled my ping. I'm getting my hello packets. In fact, let me see if I can actually suppress the hellos. Let's do undebug all and debug EIGRP packets, and let's do terse, which is basically everything except the hellos. All right, because the hellos are constant, they're going to keep annoying us. All right, so let's do a shut. This is that Ethernet interface, and what we should see here in this output, as soon as the neighbor is determined to be down, right here. Yep, right. Well, we saw the query here initially. Received a query on serial 20. So this is actually, this is the HQ router saying, hey, I lost my path. I lost my path to your loopback. Can you tell me if this is an alternate path? But I should also be sending a query once I determine that the neighbor is down. I should see sending a query. There's the received reply. There it is right here. Here's the point in which I sent the query for that particular destination. Now, if I was doing this in Wireshark, you could actually see within the Wireshark capture the actual prefix that I'm querying. There's the query, there's the acknowledgement to the query. All right, there's the reply, there's the acknowledgement for the reply. Remember, we acknowledge updates, queries, and replies. So if you look at the timestamp here, here's where the route is being, the neighbor goes down at 12:42:12:555. I send the query at 12:42:12:567. Actually, I send the query, technically I'm building the query here. I send the query at 12:42:12:587. I mean, we're talking about picoseconds here, right? Not even microseconds. I received an acknowledgement at 12:42:12:615. And I received the reply at 12:42:635. So between 587 and 635, the route is active. But as soon as I get this reply, the route goes back to passive. So even if I was lightning fast, I probably wouldn't have been able to capture the fact that the route was active, because we're talking about doing this in picoseconds. Yep. That would not be really possible. But that does demonstrate the process, and it tells you how quickly the query gets propagated and the reply gets sent. All right. So it says here, during the dual calculation, that's the time that I've sent out the query and the time I get a reply, the route goes into an active state. And of course, packets will be dropped to that destination. Now, we can look at the topology ourselves as engineers and say, well, this serial link should not get disqualified as a loop-free alternate. It should be a loop-free alternate. So what would I do to influence that? I would modify metrics. I would do something, whether it's a distribute list, offset list, whatever. I would do something to trick the branch router into thinking that this third path is a valid alternate path. Just to increase my or decrease my convergence time by as much as possible. So now if I go back to my branch and I do my show IP route, we can see that the route was actually inserted into the routing table. For that loopback, the 00 loopback, it's got the big massive metric, but not a big deal. By the way, did you fix your infinity problem?
Yes.
Okay. All right. All right. That wraps up that discovery. So we'll wrap up this recording. We'll see you guys in the next discovery. So in our last discussion in this particular section in introducing EIGRP, we're going to talk about really in quite a bit of detail the EIGRP metric and how metrics are calculated inside of EIGRP. Now, there is a somewhat complex metric that EIGRP uses to actually do the calculation. And we'll take a look at that here in a few minutes. But in classic mode, there are basically 5 different K values that are used in classic mode configuration. These K values are what we refer to as metric weights. And they're really kind of paired up with the actual metric values, bandwidth, delay, reliability, and load, to determine how much weight each of those elements of the metric have in the overall metric calculation. So the K values it says here determine which components are used for the metric calculation, but the reality is it's really the weight that we're going to apply. Now we could have a weight of 0, which means that that negates essentially that element or that component of the metric, or we can have a weight of 255, which is the maximum multiple integer that we can have for the weight calculation. Bandwidth and delay, if we use our default K values, which is K1 and K3, you can see it highlighted there in the box, but those are the ones, K1 is directly related to bandwidth and K3 is related to delay based on how the K values are applied to the formula. All right, now K1 doesn't specifically mean bandwidth, but it is a weight that is applied to bandwidth. And K3 is the weight that gets applied to delay. These K values have to match in order for EIGRP routers to become peers. If the K values don't match, then the EIGRP routers cannot establish an adjacency. Reliability and load could also be used, but again, not recommended. Cisco actually specifies on their website not to change, or as a best practice consideration, don't ever change the default K values. Let's go ahead and let the metric be calculated based on the default values. All right. Now, MTU is often listed. In fact, when you're setting up redistribution or you're trying to specify the metric that's going to be injected based on redistributing from another routing protocol, MTU is one of the last variables that you have to set. But MTU is actually not used specifically in the metric itself. It is used as a tiebreaker when we're doing ECMP or UCMP and we're trying to determine which routes are going to be actually put into the global rib if our maximum paths value is smaller than the number of paths that actually meet the condition for equal cost multipath or unequal cost multipath routing. This metric is what we refer to as a composite metric, and we use this composite metric to determine the best path to the destination. Bandwidth is the least value of the bandwidth for all the links between the routers. All right, let me actually show you what I mean by that. Let me pull up Paint here real quick, and I'll demonstrate what I mean by that statement there. So let's say that I have a router here, and I've got a link and another link and another link, and we're going to network X, and this is R1. Now, the first thing you need to know about any metric calculation, regardless of whatever that metric calculation might be, whether it's OSPF or EIGRP or ISIS, whatever it might be, is that only egress values are ever considered in the metric calculation. Ingress values are not considered as part of the metric calculation, only egress values. So when we talk about bandwidth, in the case of EIGRP, it is the worst bandwidth along the path. All right, so if this is 1 meg, and this is 10 megs, and this is 1 meg, and this is 100 meg, then ultimately the worst bandwidth is going to be 1 meg along the path, and that's going to go into your metric calculation. We'll see the formula here in a little bit. If you're considering the delay values, the delay is the cumulative delay of all of the interfaces in microseconds divided by 10, so it ultimately ends up being in tens of microseconds. So it's going to be the sum of all those delays, and then we're going to put that into the formula, and that's how we're going to calculate our delay value. But again, and this is really, really critical, only egress values are considered along the path. So if you're doing policy-based routing, or if you're doing some sort of what we call traffic engineering or route manipulation, you need to make sure that you're manipulating the values on the appropriate interfaces to affect the metric in that particular direction. So by definition, the bandwidth is the least bandwidth value of the bandwidth for all the links between the routers, which it computes essentially the metric for that parameter, and it's also considered to be throughput, right? The throughput is another term that we use. And actually in named mode, it's actually called throughput in named mode. The delay, as I mentioned before, is the cumulative delay that's obtained by the sum of the values of all the delays for all the links between the source and destination. In named mode, even though it's the same calculation, although it is done in picoseconds, it is called latency in named mode. Now, reliability and load, again, parameters that we don't typically see with the EIGRP, or at least used by default in the metric. Reliability be the worst reliability between the source and destination, and that's going to be based on active keep alives. And then the load is the worst load along the link between the source and the destination, and that's actually going to be based on the packet rate and whatever the configured bandwidth is of a particular interface. Now, MTU, as I mentioned before, also gets kind of mentioned whenever we talk about the EIGRP metric. And it is true that the MTU values do get exchanged in routing updates along with the metric components. It's never actually used for the metric calculation. It's only going to be used as a tiebreaker when the router needs to ignore specific equal cost paths to a particular destination. Let's say, for example, I have a maximum paths value of 4 set, but I actually have 6 paths that have the same metric. I have to eliminate 2 of those paths. So the paths that are going to have the highest MTU, they're the ones that are going to be preferred. Also, hop count. We saw this in the discovery as well. Hop count is exchanged as well, and that's how many layer 3 hops I have to traverse to reach a particular destination. So both of these particular values, even though they're not used to calculate this specific metric, they are used to as tiebreakers. All right, now by default, EIGRP Classic mode uses only the bandwidth and the delay to calculate the metric, but you can include interface load and reliability. And you can actually, by changing the K values, let's say I change K1 to a 5 and I make K3 or a 3, I can actually apply more weight, which is why they're called metric weights. I can apply more weight to the bandwidth option than to the delay option. But again, Cisco doesn't recommend using any of the other K values or changing the K values because, again, all the K values have to match throughout the entire autonomous system for the routers to be able to form an adjacency. All right. Now, when it comes to IPv6, we do introduce an additional K value, but very importantly, we use a 64-bit wide metric. All right, that allows us to account for more bandwidth or faster speed links, if you will. We use throughput and latency, which, by the way, are calculated exactly the same way. Throughput and latency, that's equivalent to bandwidth and delay. Even though we use different terms, it's basically the same speed. The only difference is latency is in picoseconds. And we also have this concept called rib scaling. Remember, in EIGRP for named mode, we use wide metrics. That means a 64-bit metric calculation. This allows us to have support for links that are much faster than 1 gig all the way up to terabit speeds and so on. We use the same default K values as classic mode, right? K1 and K3 are 1. Notice K6 is a 0. And that's, by the way, K6 really isn't something that necessarily changes the metric calculation. It's actually used for extended attribute support, which means K6 is usually going to be a 0 anyway. One of the issues, though, when you're using wide metrics is related to the large metric calculation for high-speed links. All right? So let's say, for example, we use the 64-bit metric for EIGRP named mode. It doesn't fit anymore in the 4-byte unsigned long value that's needed by the Cisco routing information base, meaning what goes into the global RIB, the metric value that goes into the global RIB. Now, the solution to fix this problem is to scale the route down by a size that can fit into that global routing information base. So when you do a show IP route, the metric value that you see listed there is going to be different than if you do a show IP EIGRP topology in named mode. And we achieve this by using something called the metric rib-scale. Metric rib-scale. The default value of that is 128. So we take the feasible distance, which is the overall metric in the topology database of a route, and we divide it by that metric rib scale, which is 128 by default, and that is the new value that gets assigned in the global RIB, not the EIGRP topology database, but the global RIB for a particular route. And this only applies, of course, to EIGRP routes. Okay, so you will notice that discrepancy. If you look at a show IP EIGRP topology in named mode, you'll see a very, very large integer for the feasible distance for a particular route. But then if you do a show IP route EIGRP, in the routing, in the brackets, that second number in the brackets represents the actual physical route. That's going to be a much smaller number. It's actually going to be by default 128. It's going to be divided by the feasible distance divided by 128 is going to be what that number is. All right. So the EIGRP K values are the metrics that EIGRP uses to calculate the routes. Mismatched K values, like I said, prevents neighbor relationships from being formed. Also, obviously, would then impact convergence. We can use the show IP protocol's output. We can see that on the screen here. That allows us to verify the K values that are established for a particular protocol. All right, so if you look at the formula for the calculation, we see that the metric is K1 times the bandwidth. Now, keep in mind that bandwidth is its own calculation. And this is a really important concept to understand as well. Bandwidth is 10 to the power of 7 divided by the minimum bandwidth along the path in kilobits per second. In OSPF, we use bits per second. We also use a reference bandwidth of 10 to the power of 8. But in EIGRP, we use kilobits per second. All right? Also, there's no floating point math. So, for example, if I try to do a calculation, let's say that the link speed is a T1, right? So that would be 10 to the power of 7 divided by 1544 kilobits per second. So that's 1.544 megabits per second. That would make the bandwidth metric calculation 6476 dot and whatever that number is. We don't use any floating point math in any of our metric calculations, so we always round down to the whole integer. So the actual bandwidth calculation for that particular interface would be 6476. Very important concept. We do not use floating point math in these metric calculations. So the bandwidth is 10 to the power of 7 divided by the minimum bandwidth along the path. The delay value is the sum of all of the delays, right, which is in microseconds. It is the sum of all the delays on the path, and then we divide that number by 10. The reason why I say it's in microseconds is that the delay value is actually written in microseconds on the interface. These are fixed values, by the way. The bandwidth is based on the speed or the bandwidth that's configured on the interface or the interface type. You can override that by using the bandwidth command. Or the delay is what we call serialization delay. It's a fixed value that allows us to identify how much time it takes to take data from the transmit queue and put it onto the wire as sequenced signals, right? So these are fixed values, and that's actually kind of an important thing. These are not practical throughput values because they would be dynamic by nature, and then our metric would constantly change. So you can override how the metric is calculated by overriding the bandwidth or delay calculations on the interface by using the bandwidth and delay commands. So if I go back to my formula here, the K1 is multiplied times bandwidth. And then if you look at kind of the middle section here, K2 times the bandwidth divided by 256 minus the load. K2 is 0 by default. So that section of the formula is going to get removed. K3 is 1 by default, and then the delay, like I said, is a separate delay calculation. So these are kind of sub-formulas within the formula itself. I'd notice that bandwidth and delay are the only ones that are highlighted white here because ultimately those are the only ones that are used. If K4 and K5 are not 0, we may consider reliability as part of the formula. But by default, K4 and K5 are 0, which means we negate that portion of the formula. We don't multiply by 0, we just simply eliminate that section. And then because we're going to a 32-bit wide metric, we're going to multiply by 256. That's going to give us our 32 bits. Basically, we use the same formula for metrics in IGRP, but we did not multiply by 256. In EIGRP, we multiply by 256. So we use the show interface command to see the values that are actually used as part of the metric calculation. All right. So in classic mode, that's our formula. They give us another example here. Like I said, if K4 and K5 values are set to default, which are 0, that quotient of K5 divided by K4 plus reliability, that's not used. Basically means it's set to 1. Which means ultimately that the formula is going to be reduced to bandwidth and delay times 256. And again, changing the K values is not going to be recommended. All right. So if I was to calculate, for example, the metric for an interface, I would look at that bandwidth and delay. Now, interestingly enough, if I do a show IP EIGRP topology and I drill down to a specific prefix, it will actually tell me what values are used in calculating that particular metric. All right, now you do see things like minimum MTU, You see the hop count. Again, those are used as tiebreakers in the event that there's a tie, but the total delay in this particular path is 41,000 microseconds, and the load is 121 out of 255. That's a minimum load. Reliability is 255. These are non-measured values right now because they're not used as part of the formula, so they're just kind of defaulted, but we can see what the metric is. Now, you'll notice here there are two numbers in the parentheses. We talked about this in the discovery. This is the feasible distance of a particular path. This is the reported distance of that particular path. This happens to be a connected route, so those numbers happen to be the same. All right, so the minimum bandwidth is 56 kilobits per second, and the delay is 41,000 microseconds. All right. Now, let's take a look at a couple of examples here. The path from R1 to R2 to R3 to R4. You got a bandwidth of 100 megabits per second, a delay of 40 milliseconds. Bandwidth here of 100 megabits per second, delay of 10 microseconds. Those are milliseconds, excuse me. By the way, which is a little confusing. They should have been represented as microseconds because that's how we typically see it on the interface. But in any event, we still see it listed here. And then we have 10 megabits per second. So for this top path, the worst bandwidth along that path is 10 megabits per second. So if we look at the calculation, the minimum bandwidth is 10,000 kilobits per second. Plus you take all the delays, 4,000 plus 1,000 plus 5,000. So they've already converted the milliseconds to tens of microseconds. And then you simply put those numbers into the formula. 10 to the power of 7 divided by the 10,000, multiply that times 256, 4,000 plus 1,000 plus 5,000, multiply that times 256, and you get an overall feasible distance for that particular path of 2,816,000. All right, now if I look at the bottom path, it's kind of hard to say specifically which path would be used, right? Because the bottom path has faster bandwidth, but it has higher delays, right? In fact, there's, well, overall the delays are actually smaller because the highest delay on the top path is 50 milliseconds. The smallest delay on the bottom path is 30 milliseconds. So, or the highest delay on the bottom path is 30 milliseconds. So it will appear though as though the bottom path would be the preferred path. All right, and they go through the calculations here. R1 has two different paths to reach the network behind R4. So we take into account all those different values, the delay for the top path, and this becomes the metric for the top path. And then if I consider the bottom path, the minimum bandwidth is 50,000 kilobits per second. And these are all the different delays. So the metric ends up being 1,587,200, which by the way means that in this particular case, the bottom path becomes the successor. Now we will talk about in this particular case, in this section here, in fact the next section that we're going to get into, what is feasibility condition? That's a very, very important concept to understand. I'm going to use a different diagram than the book uses to kind of describe what feasibility condition is and how it affects the dual algorithm. All right, so this is just an example of how the metric is calculated. So we're going to choose the lower path, which becomes my successor over the top path because the overall feasible distance of 1,587,200 is less than 2,816,000 along the top path. All right, you can't always assume that just because bandwidth is better or delay is better that one path is going to be chosen over the other. You have to take both variables into account. It's a very, very important concept. Now, the feasibility condition is a concept that allows us to identify a loop-free path, specifically a loop-free alternate path. OSPF actually doesn't have this characteristic, but OSPF actually introduces this concept using OSPF loop-free alternate, but it's built into EIGRP by default. Remember, EIGRP as a routing protocol doesn't have a complete picture of the topology. EIGRP only understands what the neighbors tell it, and it makes decisions based on that neighbor information. As a distance vector protocol, we do not have a complete picture of the topology. So for that reason, we have to kind of make certain assumptions. We have to evaluate alternate paths based on those particular assumptions, and that's where we talk about the feasibility condition. Let me pull up a diagram that I'm going to use to describe this concept. So here's the diagram that I like to use to describe this concept. Everything that we're going to talk about in this perspective, in this particular diagram, is going to be from the perspective of router 1 reaching this network here. Okay, so again, router 1 doesn't have a complete picture. In fact, pretty much everything beyond router 3 and router 2 is invisible to router 1, at least from the perspective of routing to network X. So that's a really, really important concept to understand. We can tell that these are distinctly unique paths and to reach router 4, which is the source of the network. But EIGRP doesn't understand that. So if we look at, first of all, which path is the successor? Now these values don't represent kind of traditional EIGRP values that you would see, but they're used for demonstration purposes. The overall feasible distance of this path is 2,000, and the feasible distance of this path is 2,500. So based on the fact that this path has a feasible distance of 2,000 and this path has a feasible distance of 2,500, the top path would be used as my successor. My successor is the best path. So that's the first thing that comes into play here. And by the way, feasibility condition is never considered when trying to determine the best path. The only thing that matters when determining the best path is the overall feasible distance of that particular path. Very, very important concept. Okay? The next thing that we consider within the EIGRP dual process is what is the advertised distance or what is the reported distance for my neighbor to reach the destination. This is where we get into trying to calculate this loop-free alternate path. If I take the reported distance of a route and I add the cost to get to my neighbor, that becomes my overall feasible distance. And that's a pretty easy concept to understand. Okay? But reported distance is used to determine whether or not the alternate path is meets the feasibility condition, if you will. Very important. Reported distance is not used to determine the best path. It is only used to determine a loop-free alternate based on the dual algorithm. Okay? So we've already chosen our best path, the green, the 2000 as the top path. That becomes my best path. That goes into my routing table and my global RIB. All right, so what is this feasibility condition? Well, R1 is trying to identify, hey, if for some reason this path fails, I would like to have a pre-selected alternate path that I've already identified as loop-free that I can immediately switch over to once my successor path fails. That path is called a feasible successor. That is the next best loop-free alternate path to the destination. But you can only become an EIGRP feasible successor if you meet the feasibility condition, and that's what this section is talking about. You meet the feasibility condition if the reported distance of that feasible successor path, which in this case is 1,500, is less than, not equal to, but less than the feasible distance of my current successor. Very, very important concept. The feasible distance of my current successor is 2,000. Does this meet the feasibility condition? 1,500 is less than 2,000, which means yes, it meets the feasibility condition, which means that this is a feasible successor path. Now, what does that mean from a convergence standpoint and from a dual process standpoint? I put this route, this successor path, into my global RIB. That becomes my normal routing path. By the way, well, I'll talk about that in a second. Let me finish this discussion here. The feasible successor is going to be in my topology database. We saw that in the discovery. If the primary path fails, I don't have to do any major dual recalculation. I can immediately start using this as my successor path without having to send a query, get a query reply, and propagate the queries down the line to the rest of the neighbors, which means that I have this very, very fast convergence scenario. But what if the path didn't meet the feasibility condition? All right, let's say, for example, this isn't 1500, maybe it's 2000, which it could be, right? Maybe that's 2000. The overall path now becomes 3000, right? So the overall feasible distance becomes 3000. We can scratch these out because those numbers might be different. They would be anyway. All right. But the bottom line is the path does not meet the feasibility condition now. 2000 is not less than 2000. It's equal. And again, equal does not qualify. So that means now in this particular case, the bottom path no longer meets the feasibility condition. What happens? Here's my successor. What happens if that path goes down? That means that I have to send a query to this peer, and that query might have to get propagated down all the way to the endpoint, saying, hey, I lost my best path. I do not have a feasible successor, but I recognize that this is a potential alternate path. Can you tell me if this path is still valid? And then the routers will send a reply in response to the query, and then that route, once I get that reply that says, hey, that route is a valid route, I will now insert this route as my new successor. And then if I have another path along the way, I'll go ahead and calculate that as potentially a feasible successor as well. So in essence, it means that EIGRP needs to just go through a secondary check to make sure that that path is still valid, because it could have been potentially part of the original path, which means that it isn't really a loop-free alternate path. It is actually technically part of the original path, meaning that if the reported distance of that secondary path is higher. Doesn't necessarily mean that's true. In this case, it isn't true, which means that that secondary path could be injected as a successor. But again, the important concept to understand here is that we have to go through that secondary check, which is going to take some additional time. We might actually run into a scenario where we go into stuck inactive, meaning that we've gone and sent our query, but we weren't able to verify the legitimacy. Maybe the replies didn't come from a particular peer, and we get to a point where we get stuck inactive. We're actually going to talk about that when we talk about the enhancements to EIGRP and adding efficiencies to EIGRP by doing things like query scoping. If a query is out there for 3 minutes, we'll get stuck inactive. We'll send a stuck inactive query after 90 seconds, but there is potential that the replies might not come in. So that is the feasibility conditions. Very, very important concept to understand. Now, as far as path calculation goes, we always select our successor path based on the shortest the shortest overall feasible distance. In this particular case, we're not looking at the feasible distance, we're looking at reported distance. And again, the whole concept of reported distance is used to determine whether or not this is a loop-free alternate path. Now, if you look at the actual feasible distance values, let me go down to the next diagram here, because it kind of gives you everything in one table. If you look at the overall metric, what we call the feasible distance, if you will, the path through router 8 has an overall path metric of 40, the path through router 2 has an overall metric of 31, and the path through router 4 has an overall metric of 140. So we know that our successor is going to be the path through router 2. It has the lowest feasible distance. The question is, do any of these other paths qualify as a feasible successor? This path does. because the reported distance of this path is less than the feasible distance of the primary path. This path does not. Now, it doesn't mean that that path ultimately couldn't be used as a path to route. It just would require the query process in order for us to be able to use that particular path. So this is what we refer to as a non-successor route, meaning that it is a potential path, but it doesn't meet that loop-free alternate concept. It doesn't meet that loop-free alternate calculation, so that means that we can't use that. Now, that also means, by the way, that if I apply a variance, this is something that we'll talk about a little bit later on. Variance is a way for us to do unequal cost multipath routing. So let's say our best metric in this case is 31. Now, if I go ahead and divide 140 by 31, that means that's 4.5 something. So I would have to apply a variance of 5 in order to potentially see that all of these paths would be used with EIGRP using ECMP, because variance is a multiplier against the best metric. So if I take, for example, 31 times 5 is 155. So any path from 31 to 155 would be considered equal, or at least usable, and then we would do some sort of unequal cost load balancing across those paths. The problem, though, is that this path does not meet the feasibility condition, which means that even though it would fall within the variance scope, it could not be used in our UCMP scenario because it isn't a verified loop-free alternate path. So only successors and feasible successors could be used automatically or even as unequal cost paths in the load balancing scenario. All right? So that's it for section number 1. We're going to go ahead and wrap up this section. We'll see you guys in section number 2, where we're going to talk about optimizing EIGRP by looking at those queries and stuck in active issues and load balancing, and we'll even take a look at some authentication in that section as well. So we'll see you guys there.